What if some of the closest places to us are the ones we understand the least? Just 240,000 miles away, half of the moon stayed hidden from human eyes for all of history. Not because we couldn't look, but because the universe wouldn't let us. And when we finally did see the far side, it raised more questions than answers. But this isn't just a story about the moon. Out there, woven into the large-scale structure of the cosmos, lies a region so empty it barely registers as part of the universe at all. A vast cosmic gap known as the Great Nothing. A place where the rules that shape galaxies seem to fall apart. So how do we even begin to understand distances like this? How do we connect lunar shadows to regions of space that stretch hundreds of millions of light years across? To answer that, we have to confront the one limit nothing can escape, the speed of light. Why does the universe impose a maximum speed? And how does that single constraint quietly determine what we can see, where we can go, and what parts of reality remain forever out of reach? From the hidden face of the moon to the deepest voids of space, this is a journey through what the universe allows us to know, and what it keeps just beyond our grasp. Before we dive into this cosmic puzzle, let's take a moment to appreciate the scale of it all. This story is travelling across the globe, reaching you right now. I'm always curious to see our small planet mapped out in the comments, so let me know which part of the world you're joining this exploration from. And if you believe these cosmic stories are worth exploring, the best way to support our mission is by liking this video and subscribing for the next one. For decades, the far side of the moon has been a realm of mystery, shrouded in shadows and secrets. Unlike the familiar cratered landscape we see from our planet, this dark side has remained largely unexplored, whispering hints of stories billions of years in the making. But now NASA's latest missions have pierced that veil of darkness, uncovering astonishing surprises that challenge everything we thought we knew about our closest celestial neighbour. From hidden water ice to strange mineral deposits and baffling geological formations, the moon's hidden face is revealing a world as alien as it is fascinating. What mysteries await on the moon's hidden far side, and why does NASA remain so captivated by it? The moon has always presented the same familiar face to those of us on Earth. For as long as human eyes have wandered skyward, we have seen its patchwork of dark, smooth volcanic plains, known as Maria, and the bright, rugged highlands marked with countless craters. This enduring familiarity is not a mere illusion of distance or lighting. It is a fundamental trait of the moon itself, a cosmic behaviour known as tidal locking. Grasping the nature of tidal locking is essential for understanding why one side of the moon remained hidden from human sight for countless millennia, wrapped in mystery until the advent of modern space exploration. Tidal locking occurs when the gravitational pull of a larger celestial body, in this case, Earth, gradually influences the rotation of a smaller orbiting body, like the moon. Over unimaginably long stretches of cosmic time, Earth's gravity exerted a subtle but relentless tug on the moon. The moon is not a perfect sphere. It has tiny bulges on the side facing Earth and the opposite side. These bulges form because Earth's gravity pulls slightly more on the near side than the far side, stretching the moon along the imaginary line connecting the two worlds. This uneven pull creates what scientists call a tidal bulge. Picture the early moon spinning far faster than it does today. As it circled Earth, the planet's gravity constantly tried to pull its bulges back into alignment, much like how Earth's gravity tugs on its oceans, producing tides. This ceaseless gravitational pull acted like a brake, gradually slowing the moon's rotation. Over hundreds of millions and perhaps even billions of years, this braking process continued. The moon's rotational energy slowly dissipated, mostly through internal friction within its rocky interior, which produced tiny amounts of heat. This process was relentless, steady, and irreversible, until the moon reached a state of equilibrium. Equilibrium occurs when the moon's rotation period, the time it takes to spin once on its axis, matches exactly its orbital period, the time it takes to circle Earth. In simpler terms, The Moon spins once in the same time it takes to complete one orbit around our planet. This perfect synchronization means that the same hemisphere always faces Earth. From our vantage point, it seems as though the Moon is not spinning at all. In reality, it is spinning, but its rotation is perfectly matched to its orbit. Imagine a person walking around a merry-go-round while always facing its center. Relative to the outside world, they rotate, but relative to the central pole of the merry-go-round, they appear stationary. For the Moon, this alignment minimizes Earth's gravitational stress, locking it in the stable, tidally locked orientation we observe today. This is not an unusual situation. Many moons across our solar system are tidally locked to their parent planets. Take Charon, the largest moon of the dwarf planet Pluto. Charon is tidally locked to Pluto, and Pluto is tidally locked to Charon. They always present the same faces to one another. Such outcomes are common when smaller bodies orbit close to massive ones over vast stretches of time. The underlying physics involves the transfer of angular momentum and the pursuit of the most energy-efficient configuration in a gravitational system. Although we generally see the same side of the Moon, over time, slightly more than 50% of its surface comes into view. This effect is due to a phenomenon called libration, a subtle wobbling or oscillation in the Moon's apparent position as seen from Earth. Several types of librations exist. Optical librations, for instance, result from the shape of the Moon's orbit around Earth. The Moon travels in an elliptical path, not a perfect circle. When it is closer to Earth, it moves a bit faster, and when it is farther away, it moves slightly slower. Yet its rotation speed remains nearly constant. This mismatch allows us occasional glimpses around its eastern and western edges, revealing a little more of its hidden terrain. Another type of libration comes from the tilt of the Moon's axis relative to its orbit. Just as Earth's tilt creates the seasons, the Moon's tilt lets us peek slightly over its north and south poles at different times. The result is that, although 50% of the Moon is always visible, and another 50% is always hidden, an extra sliver of about 9% along the edges can swing into view at certain times. Over the course of a full lunar cycle, this allows us to observe roughly 59% of the Moon's total surface, yet the remaining 41%, the far side, remains permanently invisible from Earth, a vast hidden realm that for ages stoked human curiosity. Because the far side could not be seen from Earth, its features, landscapes, and true nature remained entirely speculative for thousands of years. Ancient astronomers could map the near side in increasing detail, even giving names to craters and seas, but the opposite hemisphere was a blank canvas. No telescope, no matter how sophisticated, could bend light around the Moon to reveal the unseen half. From Galileo Galilei's rudimentary spyglass in the 17th century, to the enormous observatories of the 20th century, instruments were constrained by the Moon's tidally locked orientation. Humanity could only study what was presented. The far side steadfastly concealed itself. Early lunar maps were therefore necessarily incomplete. They showed only the visible hemisphere, leaving the far side to imagination, artistic rendering, and educated guesswork. Without direct observation, scientists could only speculate, some assuming the far side mirrored the near side, others envisioning an entirely different landscape. The invention of photography in the 19th century allowed detailed and permanent records of the near side, but it offered no insight into the hidden hemisphere. As mapping techniques improved, producing ever more intricate charts, the far side remained a mysterious void. The mystery endured because humanity lacked a crucial technological breakthrough: space travel. Until the mid-20th century, sending probes beyond Earth's atmosphere was mostly a dream confined to the pages of science fiction. The challenges were enormous: rockets powerful enough to escape Earth's gravity, guidance systems capable of precise navigation across millions of kilometers, and communication systems able to send data back from interplanetary space. These were formidable obstacles, pushing the limits of contemporary engineering and scientific understanding. The space age, ignited by the Soviet Union's launch of Sputnik 1 in the mid-1950s, changed everything. Suddenly, the impossible became achievable. The race to the Moon accelerated, driven by both geopolitical rivalry and insatiable scientific curiosity. Yet even with powerful rockets, observing the far side posed a new and immediate challenge: communication. A spacecraft on the far side would be completely blocked by the Moon itself, with no direct line of sight to Earth. Imagine trying to shout to someone on the opposite side of a huge hill. Your voice cannot travel. Similarly, any data or images collected by a far-side probe would be trapped unless a solution was devised. This led to the development of relay technologies, satellites in orbit that could catch signals from a far-side probe and transmit them back to Earth. Without such systems, long-term missions to the Moon's hidden hemisphere would have been impossible. The first successful glimpse of the far side came from the Soviet Union. In October of 1959, the Luna 3 spacecraft circled the Moon, becoming the first probe to photograph this mysterious territory. The images were crude and blurry by today's standards, distorted by early camera technology and vast distances, but they were revolutionary. They revealed a landscape far more heavily cratered than the near side, with almost no dark volcanic plains or maria. The far side was not a mirror image. It had its own distinct geological character, hinting at a separate evolutionary history. These first images sparked immense excitement, opening the door to entirely new scientific discoveries and forever changing humanity's understanding of its closest cosmic companion. The first images captured by Luna 3 were tantalizing glimpses, a tiny peek behind the Moon's shadowed veil. Yet, they were only the beginning, far from giving a complete understanding of the Moon's mysterious far side. At that time, NASA was still a young space agency, full of ambition and curiosity. Determined to explore our nearest celestial neighbour, it launched a series of missions that would lay the foundations for decades of lunar research. The Surveyor program sent uncrewed landers to gently touch down on the surface, while the Lunar Orbiter missions took high-resolution photographs, mapping the familiar near side of the Moon in preparation for human landings. These early missions focused mostly on the side visible from Earth, primarily because it was easier to land there and maintain communication. Yet scientists everywhere remained fascinated by the far side, the part that had remained hidden for millennia. Exploring the Moon required more than just powerful rockets. It demanded careful planning, inventive engineering, and years of international collaboration, and sometimes competition. The drive to uncover the unseen was not mere curiosity. It was about answering deep questions regarding the Moon's history. Was the far side older than the near side? Had it suffered a different pattern of asteroid impacts? Did it contain unique materials or geological structures that could reveal secrets about the early solar system? These questions became the fuel for exploration, shaping both scientific objectives and mission designs. NASA's approach was step by step, gradually increasing in sophistication. First came flyby missions like Luna 3, offering brief, fleeting images. Next were orbiters, which could circle the Moon and map its entire surface in detail, gathering consistent data over extended periods. The ultimate challenge was landing softly on the surface, collecting samples, and analysing them directly. Each stage built upon the previous one, improving navigation, imaging, and communication methods. Advances in miniaturized electronics, stronger antennas, and more reliable power systems were crucial. For missions targeting the far side, the challenge of communicating with Earth became especially pressing. Without a relay system to bounce signals, spacecraft could find themselves completely isolated from mission control. The importance of communication satellites, or relay satellites, cannot be overstated. Any long-term operation on the Moon's far side, whether robotic or human, depends on a network of orbiting satellites. These satellites act as middlemen, receiving data from surface equipment and sending commands back from Earth, effectively bridging the Moon's hidden side with our planet. This solution overcame a fundamental problem. The far side of the Moon can never see Earth directly, which is why it remained a mystery for so long. Exploring the far side is a testament to human persistence and ingenuity. From centuries of total ignorance, to the blurry first images, to the precise topographical maps and geological surveys of today, our knowledge has grown immensely. The far side is no longer a blank, shadowy expanse. It is a landscape filled with clues about the Moon's dramatic past, its unique geological features, and even its potential as a site for future observatories protected from Earth's radio interference. The journey to uncover its secrets has been long and challenging, but it is steadily paying off, driven by humanity's enduring desire to explore the unknown. It is remarkable to think how far we have come. from staring at a single, unchanging face in the night sky to actively mapping and studying the moon in its entirety. From the very beginning, scientists were intrigued by the stark differences between the moon's two hemispheres. The near side is dominated by vast dark plains called maria, created by ancient volcanic eruptions. These areas are relatively smooth and lightly cratered. The far side, by contrast, is rugged and heavily cratered, with only a few maria. This dramatic contrast provides vital clues about the moon's history. Scientists theorize that the near side has a thinner crust, which allowed molten lava to break through and form the maria. The far side, with its thicker crust, resisted such volcanic activity. Discovering this difference in crust thickness and composition was one of the far side's most important revelations. Subsequent NASA missions refined these theories by measuring crustal thickness and mapping the moon's elemental composition across both hemispheres. Comparing the near and far sides has revealed insights into the moon's interior and how it responded to early solar system events. In many ways, the far side is a geological Rosetta Stone, holding answers to questions about the moon's formation and early evolution. Within the massive cosmos, there are regions where galaxies cluster together in dazzling cities of light, and then there are places like the Boötes void. Stretching nearly 1 billion light-years across, this immense cosmic hollow is one of the largest known voids in the observable universe. It has been called the Great Nothing, a staggering gulf where, by all expectations, countless galaxies should be shining, yet only a scarce few can be found. What could carve out such an enormous emptiness? Is it merely a natural quirk of cosmic structure, or could something far stranger be hidden within its darkness? The name alone feels mysterious, like something drawn from an ancient myth or a tale whispered by stargazers of old. Yet it is not a story or a legend. It is real, it is vast, and it stretches across the cosmos as one of the strangest features ever discovered in the universe. When astronomers talk about it, they describe a place that seems almost impossible. A massive region of space that looks nearly empty. A yawning chasm of darkness where there should have been countless galaxies. It is not simply an ordinary gap. It is one of the largest known voids in the universe, so huge that even the human imagination struggles to grasp its immensity. The very existence of the Boötes void has fascinated scientists, stirred the curiosity of the public, and raised profound questions about how the universe is structured. Why does such emptiness exist? What does it mean for our understanding of the cosmos? And, in the quiet corners of speculation, some even wonder, could something entirely unknown dwell within that cosmic darkness? To understand why the Boötes void is so captivating, one must first picture what astronomers expect when they peer into the universe. Normally, when telescopes sweep across the heavens, their lenses and sensors capture galaxies by the millions. These galaxies are not evenly scattered, but they tend to cluster together into cosmic filaments, vast webs of light and matter that stretch across space like glowing threads. Between these filaments lie voids, the dark gaps where galaxies are sparse. Astronomers have long known that the universe is like a sponge on a cosmic scale, bright filaments and clusters of galaxies forming the solid structure, with pockets of emptiness in between. But even in these empty spaces, one still expects to find galaxies here and there. The voids are not truly void, they are just thinner regions. Yet when astronomers discovered the Boötes void, what they found stunned them. This was no ordinary empty pocket. This was a staggering desert in the sea of stars, a space so barren that it seemed unnatural. Discovered in the year 1981 by astronomer Robert Kirshner and his team, the Boötes void was found in the direction of the constellation Boötes, a region of the night sky known to stargazers since ancient times. Boötes itself is easy to spot, for it contains the bright star Arcturus, one of the most luminous stars visible to the naked eye. But behind this familiar constellation lies a secret that the human eye could never detect, an emptiness spanning roughly 330 million light-years across. To put that number into perspective, light travels at nearly 300,000 kilometers per second, and even at that blistering speed, it would take light 330 million years just to cross from one end of the Boötes void to the other. This means that the void is so vast it could contain many thousands of Milky Way-sized galaxies within it. yet only a few dozen have been found. Imagine expecting a bustling metropolis and finding only a tiny cluster of lonely villages. That is the scale of the mystery. The discovery of such a massive void was not just a curiosity. It shook the way astronomers thought about the large-scale structure of the cosmos. Scientists had already been mapping galaxies and noticing patterns of clustering, but the Boötes void seemed extreme. How could such an enormous volume of space be so empty? Was it a natural result of cosmic evolution? Or did it hint at some unknown mechanism at work? Some researchers even half-joked that if one wanted to hide an alien civilization, this would be the perfect place. So far away, so dark, so sparse that it would be beyond ordinary detection. Others speculated more cautiously, wondering if the void was simply the result of gravitational dynamics over billions of years, where matter naturally pooled into filaments and left behind regions of near emptiness. Regardless of the theories, the fascination grew. The Boötes void became a cosmic riddle, one that continues to intrigue scientists and capture the imagination of the public. Part of the allure of the Boötes void lies in the human response to emptiness. As a species, we are drawn to mysteries, and nothing is more mysterious than a silence that feels unnatural. Standing in a forest, one expects to hear the rustle of leaves, the call of birds, the hum of insects. If all falls quiet, the silence itself feels louder than any sound. The same is true with the universe. We expect to look into space and see the flicker of countless galaxies, the distant glow of star clusters, the soft haze of nebulae, when instead we see a great hollow, a cosmic silence. It feels eerie. The absence of galaxies becomes as powerful as their presence. It is like staring into a cosmic abyss that dares us to ask, why? Astronomers, of course, approach the Boötes void with the tools of science. They measure its size, estimate its contents, and try to fit it into the broader pattern of cosmic structure. But even for them, there is a sense of awe. The void is not merely large, it is staggeringly disproportionate. Its diameter of over 300 million light-years makes it one of the largest voids ever detected, occupying a volume of space so massive that it defies easy comparison. If our Milky Way galaxy were placed inside the void, it would look like a single grain of dust floating in a cathedral-sized hall. Even our local group of galaxies, the Milky Way, Andromeda, and their smaller companions, would be utterly insignificant against the backdrop of such a gulf. Astronomers sometimes call the Boötes void the Great Nothing, a title that perfectly captures both its scale and its haunting nature. The public, too, has found itself mesmerized by the Boötes void, though often for different reasons. For those who are not trained in astrophysics, the void sparks the imagination in ways that science alone cannot contain. Some see it as a terrifying abyss, a symbol of how small and fragile humanity is in the grand scheme of the cosmos. Others see it as a canvas for speculation, perhaps a place where hidden phenomena exist, undetected by our instruments. Stories and theories have sprung up, some grounded in science, others venturing into the realm of science fiction. Could the void be evidence of something artificial, as though some unimaginable force had cleared it out? Could it hide civilizations so advanced that they leave no trace? Or is it simply the universe reminding us of its vastness, its strangeness, and its indifference to our expectations? The fascination with the Boötes void is also tied to the way humans grapple with the concept of nothingness. On Earth, true nothingness is rare. Even in deserts, even in deep caves, life finds a way to fill the void. But in space, emptiness is common, and yet even there, galaxies and stars usually break up the darkness. The Boötes void stands as an extreme, an emptiness that feels almost too much to accept. When people hear the phrase 300 million light-years, their minds struggle to picture it. It is not just large, it is beyond scale, beyond comprehension. The brain, accustomed to thinking in kilometers or miles, cannot truly hold such distances, and so the void takes on an almost mythic quality, a symbol of the limits of human understanding. In that sense, it is not only a scientific puzzle, but also a philosophical one. It confronts us with the vastness of existence and asks us what it means to find so little in so much. When scientists study the Boötes void, they do so by counting the galaxies within it. The number is startlingly small, only about 60 galaxies where one might have expected thousands. That scarcity alone makes the void remarkable. It is not completely empty, but it is far emptier than theory would predict. The galaxies that are there seem lonely, drifting in an ocean of darkness without many neighbours. In most of the universe, galaxies interact, pulling on each other with gravity, colliding, merging, stirring up bursts of new star formation. But in the Boötes void, such interactions are rare. One wonders what life, if it exists in those galaxies, would think of their surroundings. Would their night skies seem darker, their view of the cosmos lonelier compared to ours? These are speculative thoughts, of course, but they add to the human fascination with the void. It is not just a feature of astronomy. It is a canvas upon which we project our curiosity, our fears, and our longing to understand the universe. The Boötes void also plays into the age-old human theme of confronting the unknown. Throughout history, explorers have set sail into uncharted seas, climbed mountains or plunged into caves, driven by curiosity and courage. Each time the unknown was both terrifying and thrilling. The Boötes void is like one of those frontiers, but on a scale that dwarfs anything on Earth. It is an uncharted sea of darkness, not to be crossed by ships or footsteps, but by the probing eyes of telescopes and the models of astrophysicists. And like all frontiers, it challenges us. It asks whether we are content with what we know, or whether we will push further into the unknown, seeking answers even when the scale seems overwhelming. The void has sometimes been painted as a place of hidden menace or great beauty. To some, it is the ultimate symbol of cosmic horror. The idea that in the great silence of the universe, there are gulfs so immense and so empty that they remind us how fragile we are. To others, it is beautiful precisely because it is so strange, a reminder that the universe is far richer and more varied than our imaginations alone could invent. Either way, the Boötes void captures something deep within the human spirit, the desire to confront mystery, even when that mystery takes the form of absence rather than presence. Astronomers continue to study the Boötes void, trying to place it within the grand tapestry of cosmic structure. The prevailing view is that it formed naturally as galaxies clustered into filaments, leaving behind great hollows. And as telescopes grow more powerful, scientists will no doubt uncover more about its contents, mapping its galaxies in greater detail, perhaps even finding faint galaxies that were missed before. Yet even if every galaxy within it were catalogued, the void would remain extraordinary. Its size and emptiness are beyond dispute, and they ensure that it will always hold a special place in both science and imagination. The discovery of the Boötes void begins in a time when the universe was still being mapped in ways that would seem slow and painstaking by today's standards, but which were revolutionary and groundbreaking for the early 1980s. In that era, the tools of astronomers were both remarkable and limited, a mixture of painstaking observation, careful recording, and ingenious deduction. The sky had long fascinated humanity, but understanding the large-scale structure of the cosmos, how galaxies, clusters, and emptiness were distributed across unimaginable distances, was only beginning to take shape. The Boötes void, one of the most astonishing and puzzling discoveries of modern astronomy, emerged from this delicate and meticulous work, revealing a void so vast and so utterly empty that it seemed almost to challenge the very imagination of scientists who first glimpsed it. The first identification of what would later be called the Boötes void took place in the early 1980s, during a period when astronomers were beginning to understand that the universe was not a random scattering of stars and galaxies, but had a structure, a sort of cosmic web. To achieve this, they employed a methodical process that involved mapping galaxies in 3 dimensions, rather than merely noting their positions in the night sky as points of light. At that time, the primary way to gauge distance was through measuring what is called redshift. Light from distant galaxies shifts toward the red end of the spectrum as the universe expands, and the amount of this redshift provides a measure of how far away the galaxy is. By measuring the redshift of hundreds, and eventually thousands of galaxies, astronomers could construct 3-dimensional maps of the universe on scales never before attempted. It was in this context that the Boötes void emerged from the data. Astronomers were conducting a survey known as the Galaxy Redshift Survey, a painstaking program of observing the light from distant galaxies, measuring the spectrum, and calculating their redshifts. In 1981, 2 astronomers, Robert Kirshner and his colleagues began analysing the results of one such survey. They were particularly focused on the large-scale distribution of galaxies in a specific region of the northern sky, an area that came to be associated with the constellation Boötes, a name which means herdsman in ancient Greek. As they charted the positions of galaxies in this region, a startling pattern began to emerge. Unlike the expected relatively uniform spread, they noticed a massive expanse where almost no galaxies seemed to exist. This void was enormous, far exceeding the sizes of previously known empty spaces between galaxy clusters. Initial calculations suggested that the region spanned roughly 250 million light-years across. To put this into perspective, our own Milky Way galaxy is about 100,000 light-years in diameter. This means that the Boötes void was 2,500 times larger than the span of our galaxy, a scale that is almost beyond human comprehension. The emptiness was so extreme that when they compared it to the number of galaxies expected based on surveys of other regions, it seemed to be missing perhaps several thousand galaxies. In an age when computers were far less powerful than today, analysing this kind of data required immense patience and care. Each measurement had to be verified, every anomaly double-checked. The possibility of observational error was a real concern. Could it be that the void was simply an artifact of incomplete data, or a result of the limitations of the telescopes used? To address these concerns, astronomers employed multiple methods. They cross-referenced their findings with different telescopes and different surveys. The surveys were conducted using wide-field optical telescopes capable of capturing large swathes of the sky in detail. In addition, spectrographs, instruments that dispersed light into its component colours, were crucial for determining the redshift of each galaxy. By systematically collecting the spectra of galaxies across this region, astronomers could calculate distances and construct a three-dimensional map. The meticulous work required patience, as each galaxy's light had to be carefully observed, measured, and recorded. Over time, as more and more data accumulated, the void's presence became undeniable. The region that had once seemed perhaps an observational fluke now appeared to be a genuine cosmic feature, a vast expanse of emptiness stretching for hundreds of millions of light-years. The discovery of the Boötes void did more than merely reveal an empty region of space. It challenged astronomers' understanding of the large-scale structure of the universe. Until then, the prevailing view was that the universe, while clumpy on small scales, would be relatively uniform when considered on larger scales. Clusters of galaxies, superclusters, and filaments were recognized, but a void of this magnitude was almost unthinkable. The existence of the Boötes void suggested that the universe had an even more complex structure than previously imagined, a cosmic web of matter and emptiness interwoven on a scale that dwarfed entire clusters of galaxies. As the 1980s progressed, additional surveys helped confirm and refine the details of the Boötes void. Astronomers continued to measure the positions and redshifts of galaxies surrounding it, and they discovered that the void was not completely empty. There were, in fact, a few scattered galaxies within its expanse, sometimes called void galaxies, which appeared isolated and strangely detached from the more densely populated regions. These galaxies were of particular interest because they provided insights into how galaxies could form and evolve in environments with so little matter nearby. The contrast between the emptiness of the void and the relative abundance of matter in surrounding regions highlighted the extraordinary scale and variety of cosmic structures. The methods used to study the Boötes void also illustrated the gradual evolution of astronomical techniques in the late 20th century. Early redshift surveys were painstaking and time-consuming, relying on long hours of observation and careful manual analysis. Each spectrum was carefully measured, often requiring photographic plates or early digital detectors to record faint signals. The advent of more advanced electronic detectors, computer-assisted analysis, and automated cataloguing would later accelerate the pace of discovery, but in the 1980s, the work was deliberate and meticulous. Astronomers often had to make repeated observations to ensure accuracy, comparing results from different nights and different instruments. The discovery of such a massive void in the process was both a triumph of careful observation and a testament to human perseverance in the face of cosmic vastness. The identification of the Boötes void also sparked debates and theories about how such a vast emptiness could exist. Was it a product of the early universe, a remnant of the primordial fluctuations that led to the formation of galaxies and clusters? Or could it have formed through the merging of smaller voids, gradually growing into a single immense expanse? These questions prompted further surveys and theoretical work, encouraging astronomers to consider not just the presence of matter, but also the distribution of the unseen, dark matter that dominates the universe's mass. Although the void appeared empty to telescopes observing visible light, astronomers speculated about the presence of diffuse gas, dark matter, or even faint undetected dwarf galaxies. Each of these possibilities required careful modelling and continued observation, expanding the horizons of cosmological research. By the end of the 1980s, the Boötes void had become a landmark discovery in astronomy, widely discussed in scientific journals and popular science publications alike. It was a symbol of the vastness and strangeness of the cosmos, a reminder that even in regions where light and matter were scarce, the universe was teeming with mysteries. The methods used to identify it, meticulous redshift surveys, careful mapping of galaxy distributions and cross-referencing multiple observations, would serve as a model for subsequent studies of large-scale cosmic structures. Researchers realized that the universe was not a uniform expanse, but a tapestry of clusters, filaments, and immense voids, with the Boötes void standing as one of the most dramatic examples of emptiness. The discovery of the Boötes void also inspired new generations of astronomers and cosmologists to probe the universe with ever greater precision. It highlighted the importance of surveying vast regions of the sky, not merely focusing on individual galaxies or clusters. Wide-field surveys, combined with spectroscopic measurements, became essential tools in mapping the cosmic web, uncovering the intricate balance between matter and emptiness that shapes the large-scale structure of the universe. The Boötes void, with its nearly 250 million light-year diameter, served as a reminder that the universe operates on scales far beyond human experience, and that even the emptiest regions can hold profound significance for our understanding of cosmic evolution. In addition, the discovery helped refine theories of cosmic evolution. The existence of such a void suggested that gravitational processes, combined with the expansion of the universe, could lead to the evacuation of matter from enormous regions, pushing galaxies into walls and filaments that outline the voids. This insight connected observational astronomy with theoretical models, illustrating how careful measurement and mapping could inform a deeper understanding of the universe's history. It became clear that voids were not mere absences but dynamic regions shaped by the same forces that create clusters and superclusters, reflecting the interplay of gravity, expansion, and the primordial seeds of structure. Even decades later, the Boötes void remains a subject of fascination. Its discovery in the early 1980s marked a turning point in how astronomers perceive the cosmos, shifting the focus from individual galaxies to the grand architecture of the universe itself. The methods developed and refined during its identification, the painstaking redshift surveys, the careful mapping, and the rigorous verification of data, set a standard for astronomical research. These techniques laid the groundwork for later surveys that would map millions of galaxies, revealing an even more intricate cosmic web and placing the Boötes void within a broader context of voids, filaments, and superclusters. The discovery of the Boötes void is a story of human curiosity and perseverance, of astronomers peering into the night sky and seeing patterns that at first seemed impossible. It is a tale of the methods and ingenuity required to detect emptiness on a scale so vast that it stretches the imagination, of the careful observations and calculations that transformed a region of the sky into one of the most famous voids in the cosmos. It reminds us that even in a universe dominated by matter, the empty spaces, those vast regions where galaxies are few and far between, hold crucial clues about the nature of cosmic evolution, the forces that shape the universe, and the very fabric of space and time. Understanding the size and scale of the Boötes void is not merely a matter of curiosity. It is central to our understanding of the universe's structure, the forces that shape it, and the mysterious processes that govern the distribution of the matter on the larger scales. When contemplating the Boötes void, one must grapple with dimensions that are so enormous that they challenge the limits of human comprehension, stretching the imagination far beyond the scale of even our most familiar cosmic structures. At its heart, the Boötes void is a vast spherical expanse nearly devoid of galaxies. To truly appreciate its enormity, one must begin by considering the size of the typical galaxy. Our own galaxy, the Milky Way, has a diameter of roughly 100,000 light-years, a distance so immense that light itself, travelling at nearly 300,000 kilometers per second, requires 100,000 years to traverse it from one edge to the other. And yet, when placed within the Boötes void, even a galaxy as grand as the Milky Way seems almost inconsequential. The Boötes void spans approximately 300 million light-years across, which is 3,000 times the diameter of the Milky Way. This means that if one could place a galaxy like the Milky Way at the centre of the Boötes void, there would still be an empty region extending 1,500 Milky Ways in every direction before encountering another significant galaxy cluster. The scale is so enormous that conventional analogies begin to fail. We are dealing with distances and volumes that defy everyday experience, entering a realm where emptiness itself becomes a dominant feature of the universe. The concept of a galaxy cluster provides another layer of context for understanding the Boötes void's magnitude. Galaxy clusters are collections of hundreds or even thousands of galaxies bound together by gravity. Some of the most massive known clusters, such as the Coma cluster or the Virgo cluster, span a few million light-years across. While these clusters contain vast numbers of galaxies, the Boötes void is nearly empty by comparison. The size of the void is roughly 100 times the diameter of a typical galaxy cluster. To imagine this, one could picture an enormous cosmic desert stretching in all directions, a region so sparse that the usual markers of galactic civilization, spiral arms, glowing nebulae, and radiant galactic cores, are almost entirely absent. Even the occasional galaxy that exists within the Boötes void is usually solitary and isolated, like a lone tree in a vast empty desert. To place the Boötes void in an even broader cosmological context, one must consider the scale of the observable universe itself. The observable universe extends approximately 93 billion light-years in diameter, a distance that encompasses all matter and energy from which light has had time to reach Earth since the universe began nearly 13 billion and 800 million years ago. In comparison, the Boötes void occupies a fraction of a percent of this observable volume, yet its relative emptiness makes it stand out like a colossal bubble within the cosmic web. While the universe as a whole is a complex network of filaments, sheets, and voids, the Boötes void is one of the largest and most striking examples of a void, making it a significant subject of study for understanding the large-scale structure of the cosmos. Its discovery challenged astronomers to rethink previous assumptions about uniformity and homogeneity on cosmic scales, prompting new theories about how matter congregates and how gravity sculpts the universe. The methods by which astronomers have measured and understood the size of the Boötes void are themselves fascinating and deeply scientific. In the early 1980s, large-scale redshift surveys became available, allowing astronomers to map the positions of galaxies in 3 dimensions rather than simply observing them in 2-dimensional projections on the sky. Redshift, which refers to the stretching of light to longer wavelengths as objects move away from us due to the expansion of the universe, provides a cosmic yardstick, enabling scientists to calculate the distance of a galaxy with remarkable precision. By compiling redshifts for thousands of galaxies, researchers could identify regions where galaxies were conspicuously absent. The Boötes void emerged clearly in these surveys as a nearly spherical region, extending roughly 300 million light-years across, devoid of the dense clustering that characterizes much of the universe. It was an observation that seemed almost paradoxical. How could such a vast empty space exist in a universe that, on smaller scales, appears so full and teeming with structure? One of the most intriguing aspects of the Boötes void is the contrast it provides with the cosmic web, the vast, intricate network of filaments and nodes formed by galaxies and dark matter. The cosmic web is a manifestation of the gravitational collapse of matter over billions of years, where galaxies and clusters form along filaments that span hundreds of millions of light-years. Between these filaments lie the voids, vast regions of low-density matter, with the Boötes void being among the most extreme examples. The void's sheer emptiness suggests that whatever matter once existed in this region either collapsed into distant filaments or was prevented from forming galaxies due to complex interactions with dark energy, cosmic expansion, or other yet undiscovered forces. Its existence challenges astronomers to understand not only the mechanics of galaxy formation, but also the subtle balance between matter, gravity, and the mysterious components of the universe that govern its expansion. Comparing the Boötes void to individual galaxies, clusters, and superclusters illuminates the profound scale differences involved. Consider a galaxy like Andromeda, slightly larger than the Milky Way, which is located roughly 2.5 million light-years away from our own galaxy. In the cosmic neighbourhood, that distance seems vast, yet it is minuscule compared to the 300 million light-year diameter of the Boötes void. Even massive clusters such as the Virgo supercluster, which contains the Milky Way, the Local Group, and thousands of other galaxies, is dwarfed by the void. The Boötes void's size exceeds that of typical superclusters, indicating that its emptiness is not merely a statistical fluctuation, but a genuine, significant feature of the universe's structure. It is as if one could remove an entire neighbourhood of superclusters and still have room for hundreds more within the void's vast expanse. Another way to grasp its scale is through volume. The volume of a sphere grows with the cube of its radius, which means that a void 300 million light-years across encompasses an incomprehensible volume of roughly 14 million cubic megaparsecs, or in more familiar terms, a number of cubic light-years that reaches beyond easy calculation. Which means that a void 300 million light-years across encompasses an incomprehensible volume of roughly 14 million cubic megaparsecs, or in more familiar terms, a number of cubic light-years that reaches beyond easy calculation. Within this space, the density of galaxies is drastically lower than the average cosmic density, often less than 1% of what is typical in the universe. Even with occasional galaxies scattered within the void, they are isolated and removed from the cosmic filaments that otherwise dominate the universe. To put this into perspective, the Boötes void is to a galaxy cluster what a single cubic metre of air is to the Earth's atmosphere, a vast empty space where the usual occupants are nearly entirely absent. The scientific implications of the Boötes void extend beyond simple size comparisons. Its existence provides critical insights into cosmology, particularly in the study of dark matter, dark energy, and the formation of large-scale structures. The standard cosmological model predicts a distribution of matter that is lumpy, with dense regions and vast voids. But the Boötes void tests the extremes of these predictions. Studying its boundaries and the few galaxies that inhabit it allows scientists to trace the forces that shape cosmic evolution. For example, galaxies near the edges of the void tend to be oriented along the filaments that bound it, hinting at the gravitational interactions that sculpt the void's shape. In essence, the Boötes void is not just empty space. It is a laboratory where the interplay of gravity, cosmic expansion, and matter distribution can be studied on the grandest of scales. Cosmic voids are among the most fascinating and mysterious features of our universe, yet they are often less understood than the bright stars, galaxies, and clusters that dominate our night sky. These enormous regions of space are, in essence, vast expanses where very few galaxies exist, a kind of cosmic emptiness that stretches across millions of light-years. Despite appearing empty at first glance, cosmic voids are crucial to our understanding of how the universe came to look the way it does today. They are not merely holes in space. They are dynamic structures that tell a story about the universe's origin, evolution, and the underlying physics that govern everything from the tiniest particle to the largest cosmic structures. To begin with, the concept of a cosmic void requires understanding what the universe looks like on its larger scales. When astronomers observe the universe, they do not see a uniform distribution of galaxies. Instead, galaxies form a web-like pattern called the cosmic web, where dense clusters of galaxies are connected by filaments and sheets of matter, and between these structures lie enormous regions of relatively empty space, the voids. These voids can range from tens of millions to over 100 million light-years across. To put this in perspective, 1 light-year is the distance that light travels in 1 year, which is roughly 6 trillion miles. Therefore, a void that is 100 million light-years across is a region so immense that even light would take 100 million years to cross it. This immense scale alone is difficult for the human mind to truly grasp, yet it is a fundamental part of the cosmic landscape. Cosmic voids are not entirely empty. They contain small numbers of galaxies, sparse clouds of gas, and dark matter, which is an invisible form of matter that does not emit or absorb light but exerts gravitational influence on visible matter. The density of these regions is far lower than that of the cosmic filaments or clusters, sometimes less than 1/10 of the average density of the universe. Despite their low density, voids are still dynamic and active regions. Galaxies within them are often smaller, less massive, and less likely to form new stars than those in denser regions. The gas in voids is thinner and cooler, and the gravitational pull is weaker, which affects how structures evolve over time. Understanding how voids form requires a look back in time to the very early universe, shortly after the Big Bang, which occurred approximately 13,800,000,000 years ago. The early universe was almost, but not perfectly, uniform. Tiny fluctuations in density existed, with some regions slightly denser and others slightly less dense. These fluctuations were incredibly small, only a few parts in 100,000, yet they set the stage for all the structure we see today. Over time, gravity acted on these differences. Denser regions attracted more matter, becoming even denser, eventually forming the stars, galaxies, and clusters we see today. Conversely, less dense regions had weaker gravitational attraction, so matter flowed away from them toward denser areas. As a result, these underdense regions grew emptier over billions of years, forming the cosmic voids we observe in the present-day universe. In essence, voids are the leftover spaces created by the gravitational sculpting of matter into filaments and clusters. The process of void formation is also influenced by the expansion of the universe. The universe has been expanding since the Big Bang, a fact first observed by Edwin Hubble in 1929 when he discovered that galaxies were moving away from us, with more distant galaxies moving faster. This expansion stretches space itself, and in underdense regions the effect is even more pronounced because there is less gravitational pull to slow it down. As a result, voids expand faster than denser regions, and their boundaries, where the sparse interior meets denser filaments, become more distinct over time. This is why voids can reach such enormous sizes, sometimes rivaling the size of superclusters of galaxies. Voids are not perfectly spherical, although early models often treated them as idealized spheres for simplicity. In reality, they are irregularly shaped, sometimes elongated or flattened, reflecting the complex distribution of matter around them. Their shapes provide valuable information about the distribution of dark matter and the overall geometry of the universe. By studying voids, astronomers can test cosmological models and gain insights into dark energy, the mysterious force that drives the accelerated expansion of the universe. Some of the largest known voids, like the Boötes void discovered in 1981, are nearly 100 million light-years across, containing only a few dozen galaxies in a region where tens of thousands might be expected based on average cosmic density. These immense voids serve as natural laboratories for studying how galaxies evolve in isolation and how large-scale cosmic structures develop over time. The study of voids also helps astronomers understand the distribution of dark matter. While dark matter cannot be seen directly, its gravitational influence shapes the cosmic web, including the formation and growth of voids. In simulations of the universe, regions with less dark matter become underdense, naturally forming voids as visible matter is pulled toward areas of higher density. This relationship between voids and dark matter provides a unique opportunity to study the invisible scaffolding of the cosmos, as the patterns and shapes of voids reflect the underlying dark matter distribution. Another important aspect of voids is their effect on the cosmic microwave background radiation, which is the afterglow of the Big Bang. As light from this radiation passes through voids, it experiences a slight change in energy due to the gravitational influence of the underdense regions, a phenomenon known as the integrated Sachs-Wolf effect. By measuring these tiny changes, astronomers can learn about the expansion history of the universe and the properties of dark energy. Voids, therefore, are not empty or irrelevant. They are active participants in the cosmic story, influencing the motion of galaxies, the propagation of light, and the evolution of cosmic structures. Void galaxies, the few galaxies that inhabit these vast empty regions, also offer intriguing insights. Because they are relatively isolated, they are less affected by the interactions and mergers that drive the evolution of galaxies in denser regions. Many of these galaxies are small, faint, and rich in gas. making them ideal laboratories for studying star formation in a pristine environment. Observations show that some void galaxies have unusual properties, such as low metallicity, meaning they contain fewer heavy elements, which suggests they have evolved more slowly than galaxies in crowded regions. By examining these cosmic outliers, astronomers can gain a deeper understanding of how the environment influences galaxy formation and evolution. The existence of voids also challenges and refines theoretical models of the universe. When large surveys of galaxies, such as the Sloan Digital Sky Survey, mapped the three-dimensional distribution of galaxies across millions of light-years, the intricate pattern of filaments and voids became apparent. These maps confirmed predictions from the theory of cosmic inflation, which posits that the universe underwent an extremely rapid expansion in its first fraction of a second. Inflation would have smoothed out the universe while leaving tiny quantum fluctuations, which eventually grew into the density variations responsible for both galaxies and voids. Therefore, voids are not random. They are the natural outcome of the physical processes that shape the universe on the larger scales. Voids also exhibit hierarchical structures. Within large voids, smaller voids can exist, creating a nested pattern sometimes described as a void hierarchy. Smaller voids expand and merge over time, similar to bubbles in a foam. This hierarchical behavior reflects the way gravity acts differently on various scales, producing a cosmic structure that is both simple in its basic principles and complex in its detailed patterns. Studying these hierarchies allows astronomers to better understand the interplay between gravity, dark matter, and the expansion of the universe. Another fascinating feature of voids is their low-velocity dispersion. In denser regions, galaxies move rapidly due to the strong gravitational pull of nearby structures. In contrast, galaxies in voids move more slowly relative to the cosmic expansion, as they are less influenced by surrounding mass. This slow motion allows astronomers to trace the history of void expansion and to measure cosmological parameters, such as the Hubble constant, in unique ways. Observations of galaxy motion within voids complement studies in denser regions, providing a more complete picture of cosmic dynamics. Cosmic voids also have implications for understanding the future evolution of the universe. As the universe continues to expand, voids are expected to grow even larger, gradually dominating the volume of space. Some models suggest that in the far future, most galaxies will be found in isolated clusters surrounded by vast empty voids, with the filaments and smaller structures becoming less connected. Studying current voids, therefore, offers a glimpse into the long-term fate of the cosmos and helps astronomers predict how structures will evolve over tens of billions of years. It is also worth noting that voids have inspired philosophical and cultural reflection. Their vast emptiness challenges our perception of the universe as a place filled with stars and galaxies. Instead, they remind us that the universe is a delicate balance between presence and absence, structure and emptiness, matter and space. The study of voids, therefore, is not only a scientific endeavour, but also an exploration of our place in a cosmos that is both immense and sparsely populated on the larger scales. The study of cosmic voids continues to advance rapidly. New surveys and powerful telescopes, both on Earth and in space, are mapping the universe in ever greater detail. Each new observation adds to our understanding of these vast emptinesses, revealing subtle patterns and structures that challenge our theories and stimulate new ideas. As we peer deeper into the cosmos, voids remind us that even in the emptiest regions, there is a wealth of knowledge waiting to be discovered, a silent yet profound testament to the universe's vast and intricate design. Cosmic voids, in their immense scale, in their quiet expanses, and in their mysterious contents, remain among the most compelling subjects in modern astrophysics. They embody the paradox of emptiness that is full of information, a paradox that drives astronomers to continue exploring, questioning, and uncovering the secrets of the universe, one void at a time. To understand its structure, and to appreciate the methods astronomers use to map it, we must begin by thinking of the universe not as a uniform, evenly filled space, but as a vast cosmic web, a complex tapestry of matter and emptiness, of galaxies and gaping voids. The universe is not a smooth soup of stars and galaxies. Instead, matter collects along enormous filaments and sheets, forming intricate networks that intersect at nodes, where clusters of galaxies gather in dense knots, leaving enormous regions between them that are comparatively empty. These empty regions are what astronomers call cosmic voids, and among them, the Boötes void stands as one of the largest and most fascinating examples ever discovered. The Boötes void, first identified in 1987 by a team led by astronomer Robert Kirshner, is a truly astonishing expanse. It is roughly 600 million light-years across, a number so vast that it is almost impossible to truly visualize. To put it into perspective, the Milky Way, our galaxy, is a mere 100,000 light-years across. That means the Boötes void is approximately 6,000 times wider than the Milky Way. Some estimates even suggest that it contains only about 60 galaxies, which is an incredibly tiny number given its immense size. In comparison, our local neighbourhood alone, the Virgo supercluster, contains thousands of galaxies. The emptiness of the Boötes void is so profound that when astronomers look into it, the light of galaxies is scarce, making it appear as a nearly black yawning chasm in the otherwise luminous fabric of the cosmos. Mapping the Boötes void was not a simple task. Astronomers rely on detailed surveys of galaxies and their positions in space to trace the large-scale structure of the universe. One of the key methods used is redshift mapping, which measures how much the light from distant galaxies has been stretched due to the expansion of the universe. The greater the redshift, the farther away the galaxy is, and by combining the positions of galaxies across the sky with their redshift distances, astronomers can construct a three-dimensional map of the universe. In the case of the Boötes void, astronomers meticulously plotted the locations of galaxies within a vast volume of space in the Boötes constellation, noting the gaps and areas where galaxies were nearly absent. This painstaking work revealed a colossal, roughly spherical region that was strikingly devoid of galaxies, a true void in the cosmic web. Interestingly, the Boötes void is not entirely empty. Although it is overwhelmingly sparse, astronomers have detected a small number of galaxies scattered throughout it. These galaxies are often isolated, living in solitary conditions far from the dense clusters and filaments that dominate other regions of space. Their isolation offers astronomers a unique laboratory for studying galaxy formation in extreme conditions. Unlike galaxies in crowded regions, which interact frequently with neighbouring galaxies, the galaxies in the Boötes void evolve with minimal external influence. This allows scientists to observe how galaxies grow and change in isolation, revealing clues about the fundamental processes that shape galactic structures over billions of years. The patterns of matter within the Boötes void are equally fascinating. While it is mostly empty, the void is not a perfect vacuum. It contains traces of dark matter, the invisible substance that exerts gravitational influence on the universe but does not emit light. Dark matter forms the scaffolding of the cosmos, guiding the formation of galaxies and the structure of filaments and voids. Even within the Boötes void, the gravitational presence of dark matter subtly influences the motions of the few galaxies that exist there. This faint web of dark matter suggests that the void, while almost devoid of luminous matter, is still part of the grand cosmic structure, connected to the surrounding filaments and clusters through gravitational threads that stretch across the emptiness. To better understand the void structure, astronomers also use simulations of the universe. These computer-generated models recreate the evolution of matter from the early universe, just after the Big Bang, to the present day. By comparing these simulations with observations, scientists can see how voids like the Boötes void naturally form. The simulations show that as matter clumps together under gravity, regions of higher density pull in surrounding material, leaving behind areas of lower density. Over billions of years, these underdense regions expand, merging with neighbouring voids to create enormous empty spaces. The Boötes void likely formed through this process, a combination of gravitational attraction and cosmic expansion sculpting the vast emptiness we observe today. Another intriguing aspect of the Boötes void is its shape. While it is often described as roughly spherical, careful mapping reveals that it is not a perfect sphere. It has irregularities, slight elongations, and variations in density. Some regions within the void are slightly denser than others, containing small filaments of matter or isolated galaxies. This uneven distribution hints at the dynamic nature of the void's formation. It is not a static, empty bubble, but a region that has evolved over billions of years, influenced by the surrounding cosmic structures and the complex interplay of gravity, dark matter, and the expansion of space itself. The Boötes void also challenges our understanding of cosmic evolution. Its sheer size and emptiness raise questions about how such a massive void could form without significant amounts of matter. Some theories suggest that it may have formed from the merging of smaller voids, each initially sparse, which over time coalesced into one gigantic region of emptiness. Others propose that rare fluctuations in the density of matter in the early universe could have led to the creation of such a vast void. While the exact details remain uncertain, the Boötes void stands as a reminder that the universe is full of extremes, regions of astonishing density and nearly unimaginable emptiness, all woven together in a delicate cosmic tapestry. Astronomers continue to study the Boötes void using increasingly sophisticated tools. Modern telescopes, both ground-based and spaceborne, allow scientists to peer deeper into the void, detecting faint galaxies and measuring their properties. Surveys like the Sloan Digital Sky Survey have provided detailed maps of millions of galaxies, giving a clearer picture of the void's boundaries and internal structure. By analysing the light from these distant galaxies, astronomers can measure their chemical compositions, star formation rates, and motions, building a detailed understanding of life inside this lonely region of space. These studies reveal that even in such a seemingly empty region, the few galaxies that exist can tell us much about the processes that govern the cosmos. The study of the Boötes void also has broader implications for cosmology, the study of the universe as a whole. Voids are sensitive to the properties of dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids expand faster than regions of higher density, their growth patterns can provide clues about the nature of dark energy. By carefully measuring the size, shape, and expansion of the Boötes void and other cosmic voids, scientists hope to test models of dark energy and gain insight into one of the greatest mysteries of modern physics. In this way, the Boötes void is not just an empty space, it is a cosmic laboratory, offering a unique window into the fundamental forces shaping the universe. Another fascinating aspect of the Boötes void is the role of cosmic filaments surrounding it. Filaments are enormous, thread-like structures of galaxies and dark matter that connect clusters across vast distances. Around the void, these filaments form a skeleton, outlining its boundaries and influencing the motion of galaxies at its edges. Galaxies at the edge of the Boötes void experience gravitational pull from these filaments, which can sometimes lead to peculiar motions or even trigger bursts of star formation. Studying these interactions helps astronomers understand how voids and filaments coexist in the cosmic web, and how the large-scale distribution of matter influences the evolution of galaxies in different environments. Interestingly, the Boötes void also has cultural and scientific significance beyond its physical properties. When it was first discovered, it captured the imagination of the scientific community and the public alike. Its enormous size and the eerie emptiness within it inspired comparisons to deserts and other vast, lonely landscapes, prompting discussions about the nature of nothingness on a cosmic scale. The void became a symbol of the universe's extremes, illustrating that space is not uniform and that the cosmos can contain regions almost entirely devoid of matter. It serves as a reminder that, even in a universe filled with countless stars and galaxies, emptiness is just as fundamental a feature as the matter that forms the familiar objects we see in the night sky. Mapping the Boötes void required extraordinary precision and collaboration. Teams of astronomers around the world pulled data from multiple surveys, carefully cross-checking observations to ensure that what appeared to be empty space was truly devoid of galaxies, not simply a result of observational limitations. This work involved not only measuring the positions of galaxies, but also correcting for effects such as cosmic dust, which can obscure distant light, and gravitational lensing, which can distort the apparent positions of galaxies. The resulting maps are among the most detailed representations of large-scale cosmic voids ever created, showing the Boötes void as a nearly spherical region, with a few isolated galaxies sprinkled within, surrounded by a dense network of filaments and clusters that define the cosmic web. The few galaxies that do exist inside the Boötes void are intriguing in themselves. They tend to be smaller, less massive, and less luminous than typical galaxies in denser regions. Some are irregular in shape, lacking the clear spiral or elliptical forms that dominate more populated areas of the universe. Their isolation allows astronomers to study galactic evolution in a nearly pristine environment, free from the gravitational interactions and mergers that shape galaxies and clusters. Observing these galaxies provides insight into how stars form, how gas flows within galaxies, and how galaxies grow in the absence of external influence. These isolated galaxies are silent witnesses to billions of years of cosmic history, living in solitude in one of the largest empty regions of the universe. Despite its emptiness, the Boötes void is an essential component of the universe's structure. Its size and presence affect the motion of surrounding galaxies, influencing the expansion of nearby filaments and clusters. The void acts like a gravitational bubble, pushing matter outward as the universe expands, contributing to the overall large-scale pattern of motion in the cosmos. Studying these motions helps astronomers understand not only the distribution of visible matter, but also the influence of dark matter and dark energy, which together make up the vast majority of the universe. In this sense, the Boötes void is far from meaningless emptiness. It plays an active role in shaping the cosmic landscape, demonstrating that even regions with very little matter can have profound effects on the universe as a whole. The discovery of galaxies inside the Boötes void was one of those moments in astronomy that completely changed how scientists thought about the universe. For a long time, when astronomers first found this enormous cosmic emptiness, they called it a void because it seemed to be utterly empty, a place where galaxies were almost entirely absent. This immense region of space, stretching over 300 million light-years across, was not merely a sparse region of stars and galaxies. It appeared at first to be a vast desert in the cosmic landscape. To early observers, the idea that such a gigantic void could exist without a single galaxy seemed almost impossible. After all, the universe is overwhelmingly made of galaxies, galaxy clusters, and filaments of matter. So to find a place that seemed completely devoid of them was like stumbling upon a desert in the middle of a bustling city, a place you could hardly believe could exist. Yet as astronomers continued to observe the Boötes void with more sensitive instruments and more careful surveys, a remarkable truth began to emerge. The void was not entirely empty. Small, isolated galaxies were scattered within its vast expanse, hiding in plain sight, waiting for the telescopes to catch them. These discoveries were surprising, because the void is enormous, with a diameter of roughly 300 million light-years, making it one of the largest known empty regions in the universe. To put this in perspective, a typical galaxy such as our Milky Way might have only a few thousand or tens of thousands of light-years across. So, the Boötes void is almost 10,000 times larger in diameter than an ordinary galaxy, and yet, even within such a massive emptiness, galaxies managed to survive and form. The first hints that the Boötes void contained galaxies came from deep surveys that carefully mapped the distribution of galaxies across the sky. Using these surveys, astronomers began to detect faint points of light where no galaxies had been expected. At first, these detections were puzzling. Scientists wondered if the signals were errors, perhaps caused by the limits of their instruments or by cosmic dust that interfered with observations. However, repeated measurements confirmed that these points of light were indeed galaxies. Slowly the void revealed its hidden structure, showing that even the most seemingly empty regions of space contain matter, even if only sparsely scattered. One of the most surprising aspects of these galaxies inside the Boötes void is their isolation. Unlike galaxies in clusters, where hundreds or even thousands of galaxies can be found in close proximity, these void galaxies are often millions of light-years away from their nearest neighbours. This means they live in an extremely low-density environment, where gravitational interactions with other galaxies are rare. In such isolation, these galaxies evolve very differently from those in crowded regions. They often appear smaller, fainter, and sometimes irregular in shape, as though their development has been shaped more by solitude than by interaction. In some cases, they have managed to retain vast amounts of gas, which in more crowded regions might have been stripped away by the gravitational pull of nearby galaxies. This abundance of gas allows them to form stars over longer periods, giving them a slow, steady pace of evolution. The discovery of these isolated galaxies inside the void also raised profound questions about how galaxies form in the first place. If galaxies need dense regions of matter to clump together, then why are there galaxies in such an extremely low-density environment? The answer lies in the nature of the universe's large-scale structure. Even in the emptiest regions, there are subtle threads of matter, invisible filaments that stretch across space, connecting one area to another. These filaments provide the seeds from which galaxies can form, even in places that appear empty. The galaxies inside the Boötes void seem to have formed along these faint filaments, surviving in isolation while the rest of the void remains mostly empty. Observing these galaxies is no simple task. Because they are few and far between, and often faint, they require powerful telescopes and sensitive instruments to detect. Astronomers have used both ground-based telescopes and space observatories to study them. Over the years, surveys such as the Sloan Digital Sky Survey, which began in 1998, have mapped large portions of the sky with unprecedented detail, revealing hundreds of previously hidden galaxies within the Boötes void and other similar cosmic voids. Each new detection adds to our understanding of the void's structure, showing that even these enormous empty regions are not completely barren, but are instead punctuated by small oases of matter, tiny islands of galaxies in a cosmic desert. The nature of these galaxies inside the void is also fascinating from a chemical and stellar perspective. Because they are isolated and evolve slowly, many void galaxies have retained their original gas compositions to a greater extent than galaxies in denser regions. This allows astronomers to study them as relatively pristine examples of galaxy evolution. Some of them have very few heavy elements, meaning they resemble the early galaxies of the universe, whose stars formed when the cosmos was still young. In this way, the Boötes void becomes not just a curiosity, but a laboratory for understanding galaxy formation, chemical evolution, and the history of the universe itself. Another intriguing aspect of void galaxies is their distribution. While the Boötes void is mostly empty, the galaxies that do exist are not entirely random in their placement. They tend to trace faint, almost invisible filaments of dark matter, the mysterious substance that permeates the universe and shapes its large-scale structure. These filaments act as cosmic scaffolding, guiding where galaxies can form and survive. The fact that even in the emptiest regions of the universe, galaxies are not randomly scattered, but instead follow these underlying structures, reveals the deep and subtle order of the cosmos. The discovery of galaxies inside the Boötes void also carries implications for our understanding of the universe as a whole. It shows that emptiness in space is not absolute. Even in regions that appear devoid of matter, small pockets of activity, islands of matter, and galaxies persist. This challenges simplistic notions of cosmic emptiness, and demonstrates that the universe's structure is far more intricate and interconnected than once imagined. The voids are not merely gaps between clusters and filaments, they are active regions in their own right, harbouring unique galaxies that tell us about the universe's history, composition, and evolution. In addition, these discoveries have prompted astronomers to look for void galaxies in other regions of space. Surveys of the nearby universe have revealed similar isolated galaxies in voids throughout the cosmos, confirming that what is seen in the Boötes void is not an anomaly, but part of a larger pattern. The universe, it seems, is a vast tapestry of matter and emptiness, where even the emptiest regions hold tiny, remarkable structures that have persisted over billions of years. Studying these galaxies also helps astronomers refine their models of cosmic evolution. Theories of galaxy formation must now account for the existence of isolated galaxies in extreme environments where gravitational interactions are minimal. This has led to improved simulations of cosmic evolution, showing how galaxies can form and survive in both crowded and empty regions, influenced by the subtle scaffolding of dark matter and the leftover gas from the early universe. The human fascination with the idea of emptiness in space takes on a new dimension with the discovery of these galaxies. What once seemed like a vast void, a nothingness stretching for hundreds of millions of light years, is now understood to contain hidden islands of light, tiny galaxies that persist despite extreme isolation. This transforms our understanding of voids from being absolute emptiness to being sparse but structured regions, a subtle network of matter punctuating a seemingly barren expanse. Astronomers continue to explore the Boötes void, and each new galaxy discovered inside it adds to our understanding of the universe's large-scale structure. The void's galaxies challenge our expectations, showing that even in the largest gaps between clusters and superclusters, the universe's creativity continues. They serve as reminders that space is never truly empty. that even in the quietest corners of the cosmos, galaxies can form, evolve, and survive for billions of years. The discovery of galaxies inside the Boötes void ultimately highlights the universe's complexity and subtlety. It shows that emptiness is relative, that the largest voids can contain small but significant structures, and that our understanding of the cosmos is always evolving. Even in a region that stretches over 300 million light-years, which initially seemed devoid of galaxies, we find life in the form of tiny, isolated galaxies, quietly moving through the darkness, slowly forming stars, and tracing the invisible threads of matter that bind the universe together. These galaxies also offer a unique perspective on cosmic time. Because they evolve more slowly, and because their environment is so different from galaxies and clusters, they preserve a kind of memory of the early universe. Observing them allows scientists to peer back in time, to understand how galaxies might have looked when the universe was only a fraction of its current age. In this sense, the Boötes void is not just a space of emptiness, but a cosmic archive, preserving clues about the formation and evolution of galaxies over billions of years. Furthermore, the study of void galaxies emphasizes the importance of careful observation and technological advancement in astronomy. Without sensitive instruments capable of detecting faint light from distant galaxies, these isolated galaxies would remain hidden, and the Boötes void would continue to be seen as truly empty. The discoveries remind us that the universe often contains surprises, and that the limits of our perception can obscure the richness of cosmic structures. In the vastness of the universe, galaxies are rarely completely alone. Most are part of an immense cosmic web, a grand tapestry woven from threads of dark matter, gas, and galaxies themselves. In this web, galaxies interact, collide, and merge, exchanging gas and dust, sparking waves of star formation, and sometimes triggering spectacular bursts of activity around their central black holes. The universe, in this sense, is more like a bustling city than a quiet countryside, full of neighborhoods where galaxies gather in clusters and groups, constantly influencing one another. Yet, amid this crowded cosmos, there are regions that seem almost eerily empty, places so vast and lonely that they appear to float in a silent cosmic ocean. These regions are known as cosmic voids, and within them lie the most isolated galaxies in the universe, galaxies living in profound solitude, cut off from the frenetic activity of the cosmic web. To understand the life of a galaxy in isolation, we must first grasp the scale and emptiness of the spaces they inhabit. Cosmic voids are enormous. They stretch across tens to hundreds of millions of light-years, spanning distances that defy human imagination. Within such voids, the density of matter, both visible and invisible, is remarkably low. While typical regions of the universe teem with galaxies, these voids may contain only a few scattered galaxies, sometimes no more than one galaxy for every 10 million cubic light-years. Imagine, if you can, being in a city with neighborhoods filled with countless people, and then stepping into an empty countryside so vast that a single individual seems almost like an intruder in a desert. This is what void galaxies experience on a cosmic scale, an existence defined by extreme isolation. Isolation affects galaxies in profound ways. Galaxies in dense regions of the cosmic web often experience gravitational tugs from their neighbours, sometimes pulling them closer until they merge, or triggering shocks in their gas that ignite waves of star formation. But a void galaxy, alone in its silent territory, is largely immune to these external influences. It does not collide with other galaxies frequently, nor does it experience the constant tidal forces that shape galaxies and clusters. Its evolution is driven almost entirely by internal processes. In a sense, a void galaxy is left to its own devices, forced to evolve slowly, quietly, and independently. While galaxies in crowded clusters may burn brightly and rapidly, consuming their gas in a flurry of star formation, a void galaxy often grows at a languid pace. Its stars form more slowly, its gas is less likely to be stripped away by interactions, and its life cycle stretches over billions of years in a more measured rhythm. The isolation of void galaxies also affects their structure and appearance. Many isolated galaxies are smaller, less massive, and more irregular in shape compared to their cluster-dwelling cousins. They often retain higher proportions of gas relative to their stars, giving them the potential to continue forming new stars for long periods. In contrast, galaxies and clusters frequently lose their gas due to interactions, halting star formation, and leaving behind older, redder stars. Observations have shown that void galaxies are often bluer, signalling ongoing star formation, albeit at a leisurely pace. Their spiral arms may be less tightly wound, and their shapes can be more chaotic, reflecting the absence of external gravitational pressures that would otherwise mould them into more orderly forms. In many ways, these galaxies are like cosmic adolescents, developing and changing slowly, shielded from the stresses of a crowded environment. Yet, isolation does not mean emptiness. Even in the deepest voids, galaxies can have companions, though they are few and far between. Some voids contain small, loose groups of galaxies, wandering together through the vast expanse. But even these groups are exceedingly sparse compared to the dense clusters found in the cosmic web. When void galaxies do interact, the encounters are rare and gentle, often insufficient to trigger the dramatic transformations seen in denser regions. Instead, these galaxies maintain their individuality, growing and evolving without being shaped or dominated by neighbours. They provide a unique laboratory for astronomers, allowing scientists to study how galaxies evolve under conditions of extreme isolation, untouched by the usual environmental pressures. The study of void galaxies also sheds light on the fundamental nature of the universe itself. Cosmologists have long known that matter in the universe is distributed unevenly. While clusters, filaments, and walls of galaxies form a complex and interconnected web, the voids are the large gaps in between. By observing the properties of galaxies in these empty regions, astronomers can test theories of galaxy formation and cosmic evolution in environments far removed from the gravitational influences and energetic interactions that dominate denser regions. For instance, by comparing the star formation rates, gas content, and chemical compositions of void galaxies with those of galaxies and clusters, scientists can identify which characteristics of galaxies are driven by nature, their internal processes, and which are shaped by nurture, the influence of environment. Void galaxies in this sense serve as a window into the most basic, unperturbed processes of cosmic evolution, offering insights that cannot be gleaned from studying galaxies in crowded cosmic neighbourhoods. Interestingly, despite their isolation, void galaxies are not entirely immune to the broader currents of the universe. Large-scale motions of matter, driven by the gravitational pull of massive structures far away, can subtly influence even these distant galaxies. Over billions of years, void galaxies may drift slowly toward denser filaments or clusters, eventually leaving the voids behind. Some may even experience interactions with the few neighbours scattered within the void, though such events are rare. Nonetheless, the vast majority of their existence is spent in solitude, evolving in a universe that seems to move around them, while they remain comparatively undisturbed in their silent cosmic homes. Astronomers have catalogued many void galaxies, thanks to detailed surveys of the sky conducted over the past several decades. One of the most notable regions studied is the Boötes void, first identified in the 1980s, a vast emptiness stretching roughly 600 million light-years across. Within this immense void, astronomers have discovered galaxies sparsely scattered throughout, providing concrete examples of cosmic isolation. Observations using advanced telescopes, both ground-based and spaceborne, have revealed that these galaxies are typically smaller and bluer than those in denser regions, confirming that their evolution proceeds at a more leisurely pace. Yet, even in this extreme emptiness, the galaxies are not completely devoid of structure. They often follow faint filamentary patterns, hinting at the subtle influence of the underlying distribution of dark matter, which guides the formation and evolution of all galaxies, even those in the deepest voids. The chemical makeup of void galaxies also reflects their isolation. Because these galaxies interact less frequently, they retain more pristine reservoirs of gas, relatively untouched by the inflow of metals and heavier elements from neighbouring galaxies. This can result in lower metallicity, meaning that the proportion of elements heavier than hydrogen and helium is smaller than in galaxies residing in clusters. Such conditions resemble those of the early universe, providing astronomers with natural laboratories to study processes similar to those that occurred in the cosmos billions of years ago, when galaxies were just beginning to form their first stars. Void galaxies, in a sense, preserve a memory of a simpler cosmic past, offering a glimpse into the unhurried evolution of matter and energy in the universe. Despite their isolation, void galaxies are not necessarily quiet. Internally, they can host dynamic processes, such as bursts of star formation triggered by internal instabilities, the collapse of gas clouds under their own gravity, or even the activity of central supermassive black holes, if they have one. However, these activities are generally less intense than those in galaxies that have been disturbed or fueled by interactions with neighbours. Star formation in void galaxies often proceeds in small localized regions rather than in galaxy-wide fireworks. Supernovae, the explosive deaths of massive stars, still occur, enriching their immediate surroundings with heavier elements, but the overall pace of chemical evolution is slower. These galaxies live in a measured rhythm, where change is slow, deliberate, and often subtle, in stark contrast to the turbulent competitive life of galaxies and crowded clusters. The study of void galaxies also challenges our understanding of what it means to be a galaxy. Traditional models of galaxy formation emphasize the role of environment, suggesting that interactions, mergers, and external influences are essential for shaping a galaxy's structure, triggering star formation, and fueling central black holes. Yet void galaxies demonstrate that galaxies can also thrive in isolation, evolving largely on their own. They can develop spiral structures, retain their gas for billions of years, and continue forming stars long after similar galaxies and clusters have exhausted their fuel. They are proof that galaxies are not merely products of their surroundings, but also capable of independent, self-directed evolution. Each void galaxy tells a story of resilience, adaptation, and survival in the face of vast emptiness. Moreover, the existence of void galaxies adds a poetic dimension to our understanding of the universe. In a cosmos dominated by immense structures, filaments, and clusters, these isolated galaxies remind us that solitude can be a defining and meaningful condition. They exist as lonely islands in a sea of emptiness, yet they shine with their own light, forging stars and evolving over billions of years with a quiet dignity. Their isolation, far from being a limitation, allows them to preserve unique characteristics and to act as natural laboratories for scientists seeking to understand the fundamental rules of cosmic evolution. Light moves at a constant speed, about 300,000 kilometers per second. But why can't anything go faster? The answer lies deep in the laws of physics. Einstein's theory of relativity showed that the speed of light isn't just fast, it's a cosmic speed limit. Nothing with mass can reach it. As objects move faster, they gain energy, and near light speed, that energy becomes infinite. It would take endless power to go faster than light, which isn't possible. This limit shapes how time, space, and even gravity work. It's why we see the universe the way it is. No matter how fast you go, light always moves away at the same speed. It's like the universe has built-in rules that everything must follow, and light speed is one of them. The concept of light and its nature has puzzled thinkers for thousands of years. Before modern science, understanding light was intertwined with philosophy, religion, and the very definition of human perception. One of the most basic questions was whether light appeared everywhere instantly, or if it took time to travel from one point to another. This debate, seemingly simple, laid the groundwork for complex scientific inquiries that would span centuries. In ancient Greece, roughly 2,500 years ago, philosophers pondered how we see. Empedocles, a Greek philosopher from Sicily who lived around 490 to 430 before Common Era, proposed one of the earliest known theories. He believed that light was not something that came from an external source and entered the eye, but rather that vision occurred because a special fire emanated from the eye itself. This fire, which he called the effluvium, would then interact with objects, allowing us to see them. Crucially, Empedocles also suggested that light was composed of tiny, rapidly moving particles. This was a radical idea for his time, implying that light had a finite speed, even if he did not propose a method to measure it. His emission theory, while incorrect about how vision occurs, contained an early inkling of light as a travelling entity. Plato, another influential Greek philosopher who lived from approximately 428 to 348 before Common Era, built upon some of these ideas. In his dialogue Timaeus, Plato described vision as a process involving three components: an internal fire from the eye that streamed forth, external light from the sun, and light reflected from objects. These three fires converged, and vision occurred at their point of union. Like Empedocles, Plato's theory also involved light moving or streaming from the eye, implying a process over time rather than an instantaneous phenomenon. However, the exact nature of this movement and its speed was not a central focus. For Plato, the philosophical implications of vision and reality were paramount. Euclid, the renowned Greek mathematician who lived around 300 to 275 before Common Era, focused less on the physical nature of light and more on its geometry. In his work, Optics, Euclid established the principle that light travels in straight lines. This was a significant observation, fundamental to understanding shadows, reflections, and the design of lenses and mirrors. While Euclid did not explicitly state that light had a finite speed, the concept of light travelling in a specific path, rather than simply appearing, subtly reinforced the idea of it being a physical phenomenon that occupied time. His geometric approach to light laid essential foundations for later optical studies. Aristotle, arguably the most influential ancient Greek philosopher who lived from 384 to 322 before Common Era, held a different view. He argued that light was not a movement of particles or waves, but rather an actuality or quality of a transparent medium. For Aristotle, light was the state of a transparent medium being illuminated, rather than something that moved through it. If a medium was transparent and a light source was present, then the medium became lightened. This perspective naturally led to the conclusion that light's appearance was instantaneous. There was no journey to be made, no speed to be measured, because it was a state, not a motion. Aristotle's immense influence meant that his view of light as instantaneous largely dominated Western thought for over 1,000 years. His authority was so great that challenging this idea was a profound intellectual undertaking. After the decline of the classical Greek and Roman empires, scientific inquiry in Europe entered a period of stagnation. However, significant advancements were made in the Islamic Golden Age. One of the most pivotal figures was Ibn al-Haytham, known in the West as Alhazen. Born in Basra in what is now Iraq in the year 965, Alhazen was a Persian polymath who made groundbreaking contributions to optics, astronomy, and mathematics. He meticulously challenged the Greek emission theories of vision. Through careful observation and experimentation, Alhazen correctly proposed that vision occurs when light from an external source reflects off objects and then enters the eye. This was a profound shift, placing the source of light outside the observer. Alhazen's work, particularly his monumental Kitab al-Manazir, Book of Optics, written between 1011 and 1021, was revolutionary. He conducted experiments with pinhole cameras, demonstrating how light rays travel in straight lines. While he acknowledged that light must travel, he too struggled with the immense speed of light, and did not conclude that it had a finite, measurable speed in the way later scientists would. He understood that if light was instantaneous, it would not explain certain observed phenomena, yet he did not definitively state it had a measurable speed. Nevertheless, his empirical approach, emphasis on observation and experiment, and his correct understanding of how vision occurs were critical steps forward, moving the study of light from pure philosophy to experimental science. His work influenced European scholars for centuries after being translated into Latin in the 12th century. During the European Renaissance and the scientific revolution of the 16th and 17th centuries, the question of light's speed re-emerged with renewed vigour. The prevailing Aristotelian view of instantaneous light still held considerable sway, but new methods of scientific inquiry and a growing emphasis on experimentation began to challenge old dogmas. René Descartes, the influential French philosopher and mathematician, living from 1596 to 1650, also contributed to the discussion. Descartes viewed light as a pressure or tendency to move through a perfectly rigid and continuous medium that filled all space, which he called plenum. In his theory, the transmission of this pressure was instantaneous, much like how a push applied to one end of a rigid rod would immediately transmit to the other end. For Descartes, light did not travel in the sense of motion taking time. Rather, it was an immediate propagation of a state. While his concept of light's instantaneous nature aligned with Aristotle, his idea of a physical medium through which light operated foreshadowed later ideas about the ether. Descartes' influence on scientific thought was immense, and his instantaneous view of light was widely accepted among his followers. It was against this backdrop of philosophical speculation and a prevailing belief in instantaneous light that the first truly scientific attempt to measure its speed was made. This monumental effort was undertaken by Galileo Galilei, the renowned Italian polymath who lived from 1564 to 1642. Galileo is often credited with ushering in the era of modern experimental science, and his curiosity extended to the speed of a light. Galileo, unlike his predecessors, was not content with mere philosophical arguments. He believed that if light had a finite speed, however fast, it should, in principle, be measurable. His approach was pragmatic and ingenious for his time, despite its ultimate failure to yield a precise measurement. The experiment, likely conceived around 1638 and described in his posthumously published discourses and mathematical demonstrations relating to two new sciences, involved two observers with lanterns. The setup was relatively simple in concept. Galileo proposed that two individuals, each equipped with a lantern that could be quickly covered and uncovered, position themselves at a significant distance from one another. Let's imagine Galileo himself and an assistant. The first observer, Galileo, would uncover his lantern. As soon as the second observer, the assistant, saw the light from Galileo's lantern, he would immediately uncover his own lantern. The first observer would then measure the time it took from when he first uncovered his lantern until he saw the light from the assistant's lantern. The total time measured would represent the time it took for the light to travel from Galileo to the assistant, plus the time it took for the assistant to react and uncover his lantern, plus the time it took for the light to travel back from the assistant to Galileo. By conducting the experiment over different distances, Galileo hoped to isolate the time taken for light's travel. For instance, if they performed the experiment over 1 mile and then over 10 miles, the difference in the measured times, after accounting for human reaction time, would, in theory, reveal the time light took to cover the additional distance. Galileo described the experiment as follows. Let the two observers be at a distance of a few miles, say 1 or 2. Let each provide himself with a lantern so arranged that its light is covered or uncovered by the interposition of the hand. Let one of them, say A, at a given instant expose his light. The other, B, who perceives it, is to expose his own light at the very instant he sees that of A. A, in turn, is to note the instant when he sees the light of B. The interval between the instant when A exposes his light and the instant when he sees that of B, deducting the time required for B to expose his light, will give the time consumed by the light in passing to and fro over the interval between A and B. Galileo and his assistant attempted this experiment, first over short distances on land, and then reportedly over greater distances, perhaps even between two hills separated by several miles. They found that for any practical distance they could manage, the measured time interval was indistinguishable from what they observed when they were very close to each other. In other words, the time it took for light to travel the distance was far too short to be distinguished from the reaction time of the human observers. The human reaction time, which is typically a few tenths of a second, completely dwarfed the actual travel time of light over such distances. Galileo concluded that if the light did have a finite speed, it must be extraordinarily fast, far too rapid to be measured with the technology and methods available to him. He famously stated, "I have tried the experiment, and the result was that it was impossible to discern whether the light of the first lantern was seen at the instant of its exposure, or whether it travelled from the one place to the other with a perceptible interval of time." While he did not succeed in measuring the speed of light, his experiment was immensely significant. First, it represented a crucial shift in scientific methodology. Instead of relying on philosophical deduction or religious dogma, Galileo adopted an empirical approach, attempting to measure a physical phenomenon. This was a hallmark of the burgeoning scientific revolution. Second, his experiment, despite its negative result, did not prove that light was instantaneous. Instead, it strongly suggested that if light had a speed, it was so incredibly high that human perception and simple mechanical means could not detect the delay. This kept the question of light's finite speed alive and spurred future generations of scientists to devise more sophisticated methods. It moved the problem from the realm of philosophical speculation to that of experimental physics. The challenge of measuring such an immense speed was daunting. Even today, the speed of light is so fast that it seems instantaneous in our everyday experience. Light travels from the Sun to Earth, a distance of about 93 million miles, in approximately 8 minutes and 20 seconds. For a light signal to travel even 1 mile and back, it would take roughly 11 millionths of a second. A human reaction time is orders of magnitude slower than this. Galileo's ingenuity was in even conceiving such an experiment, given the limitations of the clock technology of his era. Accurate timekeeping devices like pendulum clocks were only just being developed around this time, and their precision was still limited. Following Galileo's pioneering, albeit inconclusive attempt, the idea that light might have a finite speed continued to gain traction among some scientists. However, definitive proof and an actual measurement would not come for several more decades. This would require observations on a cosmic scale, leveraging the vast distances of the solar system. The first successful measurement of the speed of light came from the Danish astronomer Ole Roemer in 1676. Roemer was observing the eclipses of Io, one of Jupiter's largest moons. Io orbits Jupiter, and from Earth, we can observe it periodically disappearing behind Jupiter, an eclipse, and reappearing. Roemer noticed a systematic variation in the timing of these eclipses. When Earth was moving away from Jupiter in its orbit, the eclipses appeared to be delayed. When Earth was moving towards Jupiter, the eclipses appeared to occur earlier than predicted. Roemer correctly deduced that these discrepancies were due to the finite time it took for light to travel the varying distances between Earth and Jupiter. The light had to travel an extra distance when Earth was further away, causing a delay in observation. By observing these delays over many months, Roemer calculated that it took light approximately 22 minutes to cross the diameter of Earth's orbit. While his estimate for the Earth-Sun distance, and thus the diameter of Earth's orbit, was not perfectly accurate by modern standards, and his resulting speed of light was about 25% lower than the accepted value today, his method was sound. He established, beyond reasonable doubt, that light had a finite, measurable speed. This was a monumental achievement, finally laying to rest the centuries-old philosophical debate. It proved that light was not an instantaneous phenomenon, but something that travelled across space and took time to do so. Following Roemer's breakthrough, other scientists would devise increasingly precise methods to measure light's speed, using both astronomical and terrestrial approaches. These future experiments, building on the foundation laid by Galileo's conceptual attempt and Roemer's initial success, would refine our understanding of this fundamental constant of the universe. The early ideas, from ancient philosophical musings to Galileo's practical experiment, were essential steps in shifting human understanding of light from an abstract quality to a measurable, physical phenomenon, paving the way for the profound discoveries of later centuries. The evolution of thought from ancient times concerning light was a gradual process, moving from highly speculative philosophical positions to more empirical and quantitative ones. The challenge was immense because light's speed is so great that it defies everyday human experience. For most of human history, the idea of light travelling at a finite speed seemed counterintuitive. If you lit a candle, the room appeared to be illuminated immediately. There was no perceptible delay. This everyday observation strongly supported the Aristotelian view of instantaneous illumination. However, as observational tools improved and as scientific methodology became more rigorous, particularly during the scientific revolution, the instantaneous view began to face scrutiny. Galileo's attempt, while unsuccessful in measurement, was crucial because it introduced the idea that a natural phenomenon, even one as fleeting as light, could be subjected to experimental verification. It planted the seed that the answer lay not in philosophical debate, but in careful observation and measurement. The failure of his experiment, therefore, was not a failure of the hypothesis, but a testament to the immense speed of light and the limitations of the available technology. The conceptual shift from instantaneous to finite speed was not merely an academic exercise, it had profound implications for how the universe was understood. If light had a speed, it meant that when we looked at distant stars, we were seeing them not as they are now, but as they were when the light left them. This idea, which is commonplace today, was revolutionary. It introduced the concept of looking back in time by observing the cosmos, an idea that would later become central to astronomy and cosmology. The early work on light, though often primitive by modern standards, created the intellectual scaffolding upon which future theories and experiments would be built. From the initial philosophical debates of the Greeks to the empirical attempts of Galileo and the astronomical observations of Roemer, each step contributed to a clearer, more precise understanding of light's nature. This progression from pure thought to attempted measurement, even if initially frustrating, underscored a fundamental principle of science, that even the most seemingly instantaneous phenomena might, upon closer inspection and with better tools, reveal a finite, measurable quality. The journey to understand why light has a speed limit truly began with these foundational questions, and the tireless efforts of early thinkers to answer them. The simplicity of the question belied the complexity of the phenomenon and the experimental challenges it posed for centuries. The conceptual leap from light as an immediate presence to light as a travelling entity was one of the first major breakthroughs in understanding its fundamental properties. The nature of light has been a subject of intense scientific debate for centuries. Is light a stream of tiny particles, or does it behave like a wave, similar to ripples on water or sound travelling through air? This question, seemingly straightforward, led to a long-standing scientific controversy that spanned from the 17th century well into the 20th century, ultimately revealing a deeper, more complex reality. The arguments for each view were compelling, supported by observations and experiments that, at different times, seemed to favour one over the other. In the 17th century, two prominent theories emerged to explain the behaviour of light: the corpuscular theory and the wave theory. Leading the charge for the particle view was the towering figure of Isaac Newton, the English physicist and mathematician who lived from 1642 to 1727. Newton, whose work fundamentally reshaped physics with his laws of motion and universal gravitation, proposed that light consisted of a stream of extremely small discrete particles, which he called corpuscles. Newton's corpuscular theory explained several observed phenomena very elegantly. For instance, the phenomenon of reflection, where light bounces off a surface, could be easily understood. If light was made of particles, then when these particles struck a smooth surface, they would bounce off in a predictable manner, much like tiny billiard balls. The angle at which they hit the surface would be equal to the angle at which they bounced off, perfectly consistent with the law of reflection. Refraction, the bending of light as it passes from one medium to another, for example, from air into water, was also explained by Newton's theory. He proposed that when light corpuscles entered a denser medium, they experienced a force that pulled them towards the normal, an imaginary line perpendicular to the surface. This force would cause the particles to accelerate, meaning they would travel faster in the denser medium. Therefore, according to Newton's corpuscular theory, light should travel faster in water or glass than in air. This specific prediction would later become a crucial test between the wave and particle theories. Another strong point in favour of the corpuscular theory was its ability to explain the formation of sharp shadows. If light travelled as distinct particles in straight lines, then when these particles were blocked by an opaque object, they would cast a clear, sharp shadow with a distinct boundary between light and dark. This was precisely what was observed in everyday life. The concept of light travelling in straight lines, known as rectilinear propagation, was a natural consequence of the particle view. Newton's immense scientific authority and the success of his other theories meant that his corpuscular theory of light gained widespread acceptance, particularly in England, and dominated scientific thought throughout the 18th century. His detailed studies of prisms, demonstrating how white light could be split into a spectrum of colours and then recombined, also fit well with his particle view, suggesting that different colours were associated with different types or sizes of corpuscles. However, at roughly the same time Newton was developing his corpuscular theory, a competing idea was being proposed by Christian Huygens, a Dutch physicist, astronomer and mathematician who lived from 1629 to 1695. Huygens advocated for a wave theory of light. He proposed that light was not a stream of particles, but rather a series of waves or vibrations that propagated through an invisible, elastic medium that filled all space, which he called the luminiferous ether. Huygens' wave theory was based on his principle, now known as Huygens' principle. This principle states that every point on a wavefront, the leading edge of a propagating wave, can be considered as a source of new spherical wavelets. These wavelets expand outward, and the new wavefront is formed by the envelope of all these secondary wavelets. This principle allowed Huygens to explain reflection and refraction from a wave perspective. For reflection, Huygens showed that if waves struck a surface, the secondary wavelets would combine to form a reflected wavefront, obeying the law of reflection. For refraction, his wave theory predicted something different from Newton's particle theory. When a light wave entered a denser medium, like water, Huygens argued that the wave's speed would decrease. The change in speed would cause the wavefront to bend, leading to refraction. This was a direct contradiction to Newton's prediction that light would speed up in a denser medium. This difference in prediction concerning the speed of light in different media would later become a decisive experimental test. Huygens' wave theory also provided a natural explanation for phenomena like diffraction, where light seemed to bend around obstacles or spread out after passing through small openings. While Newton's particle theory struggled to explain why light didn't always cast perfectly sharp shadows and sometimes showed slight spreading, the wave theory could account for this bending behaviour, similar to how water waves spread out after passing through a gap. However, the evidence for diffraction was not as clear-cut in the 17th century, and the effects were often subtle, making the particle explanation of sharp shadows seem more convincing to many. The primary challenge for Huygens' wave theory was the concept of the ether. If light was a wave, what was it waving in? Sound waves need air or another medium to travel. Water waves need water. If light travelled through the vacuum of space, then the ether had to be present everywhere, including within what seemed to be empty space. Describing the properties of this invisible, undetectable medium that could transmit light waves at such high speeds became a significant hurdle for the wave theory. Furthermore, the wave theory struggled to explain why light seemed to travel in straight lines and cast sharp shadows, given that waves tend to spread out more. Throughout the 18th century, Newton's colossal reputation meant that his corpuscular theory largely overshadowed Huygens' wave theory, particularly in England. Scientists continued to refine optical instruments based on the principles of light travelling in straight lines and behaving like particles. The wave theory, despite its elegant explanations for some phenomena, remained a minority view. However, the tide began to turn dramatically in the early years of the 19th century, thanks largely to the work of a brilliant English polymath named Thomas Young, who lived from 1773 to 1829. Young, a physician, physicist, and linguist, provided compelling experimental evidence that strongly supported the wave nature of light. Young's most famous experiment, often called the double-slit experiment, provided irrefutable evidence of light's wave-like behaviour. In 1801, Young devised an experiment where he allowed a beam of light to pass through two very narrow, closely spaced slits. If light were made of particles, he reasoned, these particles would simply pass through the slits and create two bright lines on a screen behind them, corresponding to the two slits. However, what Young observed was entirely different. Instead of two bright lines, he saw a pattern of alternating bright and dark bands or fringes. This interference pattern was a hallmark of wave behaviour. When two waves meet, they can either reinforce each other, constructive interference, leading to a brighter region, or cancel each other out, destructive interference, leading to a dark region. This is precisely what happens with water waves or sound waves. Young's experiment demonstrated that light waves, after passing through the two slits, interfered with each other, producing the observed pattern of bright and dark fringes. This phenomenon was impossible to explain with particles travelling in straight lines. The experiment provided strong evidence that light was indeed a wave. Young also worked on the phenomenon of diffraction, further demonstrating how light could bend around corners or spread out after passing through small apertures, producing patterns that could only be explained by the wave nature of light. His work, along with his explanation of colour perception based on 3 primary colours, significantly revived the wave theory. Around the same time, independently and with powerful mathematical rigour, the French engineer and physicist Augustin Jean Fresnel, who lived from 1788 to 1827, also developed a comprehensive wave theory of light. Fresnel's work was particularly strong in explaining diffraction and interference patterns with mathematical precision. He refined Huygens' principle, providing a more robust mathematical framework for how waves propagate and interfere. One of the most striking confirmations of Fresnel's wave theory came from an unexpected source. Siméon Poisson, a French mathematician who was initially a critic of Fresnel's wave theory, deduced a seemingly absurd prediction from Fresnel's equations. Poisson calculated that if a perfectly opaque circular obstacle was illuminated by a point source of light, then according to the wave theory, there should be a tiny bright spot precisely at the centre of the shadow cast by the obstacle. This prediction, derived purely from mathematical theory, seemed counterintuitive for a phenomenon traditionally associated with sharp shadows. However, in 1818, François Arago, another French physicist, performed the experiment and indeed observed the bright spot, which came to be known as the Poisson spot, or Arago spot. This striking experimental confirmation provided powerful evidence in favour of Fresnel's wave theory and against the simple particle view. Another important phenomenon that strongly supported the wave theory was polarization. Light can be polarized, meaning its vibrations occur in a specific plane. For example, when light passes through certain crystals, it can be split into 2 beams, each polarized in a different direction. This behavior was difficult to explain with simple, spherical particles. However, if light was a transverse wave, meaning its oscillations are perpendicular to the direction of propagation, like waves on a string, then the different planes of vibration could easily account for polarization. This distinction between longitudinal waves, like sound, where oscillations are parallel to propagation, and transverse waves became crucial in the development of the wave theory. Thomas Young was among the first to suggest that light waves must be transverse. By the mid-19th century, the experimental evidence in favour of the wave theory had become overwhelming. Young's interference experiments, Fresnel's detailed mathematical framework, the confirmation of the Poisson spot, and the elegant explanation of polarization all pointed strongly towards light behaving as a wave. The final nail in the coffin for Newton's idea that light travels faster in denser media came from Hippolyte Fizeau and Léon Foucault, French physicists. Fizeau, in 1850, performed an experiment that compared the speed of light in air and water. He used a rotating toothed wheel to chop a beam of light, sending it over a long distance and back. Foucault, in 1862, refined this method using rotating mirrors. Their experiments definitively showed that light travels slower in water than in air. This direct experimental result perfectly matched the prediction of Huygens' wave theory and directly contradicted Newton's particle theory. This was a decisive victory for the wave model. With the success of the wave theory, the scientific community largely accepted that light was a wave. The focus then shifted to understanding the nature of the ether through which these waves were supposedly propagating. If light was an electromagnetic wave, as Maxwell would later show, and it needed a medium, then the ether had to possess very specific and increasingly problematic properties. It had to be rigid enough to support very high-frequency vibrations, the waves of light, and therefore very high speeds, yet it also had to be tenuous and invisible enough to offer no resistance to planets moving through it. This conceptual difficulty would set the stage for the next great revolution in physics. Despite the strong evidence for the wave theory, the story of light's nature was not yet complete. Certain phenomena, particularly those involving the interaction of light with matter at the atomic level, would later prove difficult to explain solely with a wave model. The photoelectric effect, for example, where light causes electrons to be ejected from a metal surface, could not be adequately explained by the wave theory. This phenomenon suggested that light also behaved as if it were made of discrete packets of energy. This would eventually lead to the concept of wave-particle duality, proposed in the 20th century, which states that light exhibits properties of both waves and particles, depending on how it is observed or interacted with. The historical debate between the wave and particle theories of light was a classic example of scientific progress. It was not a simple case of one theory being entirely right and the other entirely wrong. Both theories had strengths in explaining certain aspects of light's behaviour. Newton's particle theory offered intuitive explanations for reflection and sharp shadows, and held sway for a long time due to his authority. However, as new experimental techniques emerged, and phenomena like interference, diffraction and polarization were meticulously studied, the wave theory provided more consistent and comprehensive explanations. The decisive experimental results, particularly those related to interference patterns and the speed of light in different media, ultimately tipped the scales in favour of the wave model in the 19th century. This intellectual journey highlighted the critical role of experimental evidence in resolving scientific controversies and pushing the boundaries of human understanding. The debate set the stage for later breakthroughs that would reveal the true, dual nature of light. The journey to accurately measure the speed of light is a testament to human ingenuity and the relentless pursuit of precision in science. For centuries it was believed by many, including influential thinkers like Aristotle and Descartes, that light propagated instantaneously across any distance. However, as scientific methods evolved, a different view began to take hold. The idea that light, like everything else, possessed a finite speed, however incredibly fast. The challenge then became not just to theorize this, but to prove it through observable phenomena and precise measurements. The story of measuring light's speed is a narrative of improving technology, clever experimental design, and the slow but sure convergence on a universally accepted value. The very first compelling evidence that light had a finite speed, rather than being instantaneous, came from the realm of astronomy in the late 17th century. This groundbreaking discovery was made by the Danish astronomer Ole Roemer, who lived from 1644 to 1710. Roemer was working at the Paris Observatory, where he was meticulously observing the moons of Jupiter. Specifically, he focused on Io, the innermost of Jupiter's 4 largest moons, which was known for its relatively quick orbital period and frequent eclipses. An eclipse occurred when Io passed behind Jupiter, disappearing from Earth's view and then reappeared. These events were predictable based on Io's known orbit around Jupiter. Roemer, along with his supervisor Giovanni Domenico Cassini, had compiled extensive tables predicting the times of Io's eclipses. However, as they continued their observations over many months, Roemer noticed a peculiar and systematic pattern in the timing of these eclipses. He observed that the predicted times of Io's reappearances from behind Jupiter were not always accurate. When Earth was moving away from Jupiter in its orbit around the Sun, the eclipses seemed to occur later than predicted. Conversely, when Earth was moving towards Jupiter, the eclipses seemed to occur earlier than predicted. The maximum delay or advance in timing that Roemer observed was about 11 minutes when Earth moved from its closest point to Jupiter to its furthest point from Jupiter. Roemer correctly deduced that these variations could only be explained if light took a finite amount of time to travel the changing distance between Earth and Jupiter. As Earth moved further away from Jupiter, the light from Io's reappearance had to travel a greater distance to reach Earth, causing a delay in its observation. When Earth moved closer, the distance light had to travel decreased, causing the eclipses to appear earlier. He reasoned that the accumulated delay over several months, as Earth moved from its position closest to Jupiter to its position farthest from Jupiter, was due to the extra distance light had to cover across Earth's orbit. In a presentation to the French Academy of Sciences in 1676, Roemer explained his findings. He calculated that light took approximately 22 minutes to cross the diameter of Earth's orbit. At that time, the exact diameter of Earth's orbit was not known with high precision. Based on his 22-minute estimate and the best available estimates for the size of Earth's orbit, Roemer calculated the speed of light to be roughly 210,000 kilometers per second, or about 130,000 miles per second. This was a remarkable achievement. While his value was about 25% lower than the currently accepted speed, his method was sound, and his discovery provided the first definitive experimental proof that light travels at a finite speed, ending centuries of speculation. It opened up a whole new area of scientific inquiry. Despite Roemer's compelling evidence, his discovery was not immediately and universally accepted. Some prominent scientists, including his former mentor Cassini, remained skeptical, preferring to attribute the observed discrepancies to irregularities in Io's orbit rather than the finite speed of light. However, over time, as further astronomical observations confirmed the pattern Roemer had identified, his explanation gained wider acceptance. James Bradley, an English astronomer, further solidified the idea in 1728 through his discovery of stellar aberration, which was another astronomical phenomenon that could only be explained by light having a finite speed and Earth moving through space. For nearly 2 centuries after Roemer, efforts to measure the speed of light shifted from astronomical observations to terrestrial experiments. The goal was to conduct measurements entirely on Earth, providing a more controlled environment and potentially greater precision. This was a significant challenge because, even over distances achievable on Earth, light travels incredibly fast, making the time intervals extremely short and difficult to measure with the available technology. Precise clocks, optical instruments, and clever experimental setups were needed. The first successful terrestrial measurement of the speed of light was performed by the French physicist Hippolyte Fizeau, who lived from 1819 to 1896. Fizeau's experiment, conducted in 1849, was a landmark achievement. It was the first time the speed of light was measured without relying on astronomical distances. Fizeau's setup was ingenious. He used a rapidly rotating toothed wheel, much like a gear with many teeth and gaps. A beam of light was shone through one of the gaps in the wheel. After passing through the gap, the light travelled a significant distance, reflected off a mirror, and then returned along the same path. The crucial part of the experiment was that this returning light had to pass back through the same gap in the rotating wheel to be observed by Fizeau. The experiment worked like this. A light source was positioned so that its beam passed through a gap between 2 teeth of the rotating wheel. The light then travelled about 8,633 metres, about 5.36 miles, to a distant mirror. The mirror reflected the light back towards the rotating wheel. If the wheel was rotating at a certain speed, by the time the light returned, the gap it had originally passed through might have moved on, and a tooth might now be in its place, blocking the light from reaching the observer. However, if the wheel rotated at a specific faster speed, the next gap would precisely align with the returning light, allowing it to pass through to the observer. By slowly increasing the rotation speed of the wheel, Fizeau could observe when the returning light was first blocked, by a tooth moving into the path of the original gap, then when it reappeared, when the next gap aligned, then when it was blocked again, and so on. By measuring the speed of the wheel's rotation at which the light was blocked or reappeared, and knowing the number of teeth on the wheel, Fizeau could calculate the time it took for the light to travel to the mirror and back. Knowing the total distance travelled, twice the distance to the mirror, he could then calculate the speed of light. Fizeau's toothed wheel had 720 teeth. He found that at a rotation speed of approximately 12.6 revolutions per second, the returning light was completely blocked by a tooth. At twice that speed, or about 25.2 revolutions per second, the light reappeared, meaning the next gap had moved into position. Using these measurements, Fizeau calculated the speed of light to be 315,000 kilometers per second, 195,728 miles per second. This was very close to the modern accepted value, and significantly more accurate than Roemer's astronomical measurement. Fizeau's experiment was a triumph of terrestrial measurement, showing that the speed of light could be determined with precision on Earth. Just a few years after Fizeau, another French physicist, Léon Foucault, who lived from 1819 to 1868, developed an even more precise method for measuring the speed of light. Foucault's experiment, performed in 1862, utilised a rapidly rotating mirror instead of a toothed wheel. This method was technically more challenging but offered greater accuracy. In Foucault's setup, a beam of light from a source was directed to a rapidly rotating mirror. As the mirror spun, it reflected the light beam towards a stationary mirror located a considerable distance away. After reflecting off the stationary mirror, the light travelled back to the rotating mirror. During the time it took for the light to travel to the stationary mirror and back, the rotating mirror would have spun through a small angle. Because the mirror had rotated, the returning light beam would be reflected at a slightly different angle compared to the initial outbound beam. This slight deflection of the returning beam was then measured. By precisely measuring the angle of deflection of the returning light and knowing the speed of the mirror's rotation and the distance to the stationary mirror, Foucault could calculate the time it took for the light to make the round trip. From this time and the known distance, he could determine the speed of light. Foucault's experiment yielded a value of 298,000 kilometers per second, 185,177 miles per second. This result was even closer to the modern accepted value than Fizeau's. Foucault's method had another profound impact beyond just providing a more accurate measurement. He also used his apparatus to compare the speed of light in air and in water. His experiments unequivocally demonstrated that light travels slower in water than it does in air. This finding was extremely significant because it directly contradicted Isaac Newton's corpuscular, particle theory of light, which predicted that light particles should speed up in a denser medium like water. Conversely, Foucault's results strongly supported Christian Huygens' wave theory of light, which predicted that light waves would slow down when entering a denser medium. Foucault's experiment thus provided crucial evidence that solidified the wave theory of light as the dominant paradigm in the 19th century. Towards the end of the 19th century, and into the early 20th century, the American physicist Albert Abraham Michelson, who lived from 1852 to 1931, dedicated much of his career to achieving even greater precision in measuring the speed of light. Michelson's work was meticulous and groundbreaking, and he became renowned for his highly accurate measurements. Michelson initially refined Foucault's rotating mirror method. In 1879, he conducted experiments at the United States Naval Academy in Annapolis, Maryland, using an improved version of Foucault's apparatus. He placed the distant mirror approximately 600 meters, about 2,000 feet, away. His measurements yielded a value of 299,910 kilometers per second, 186,377 miles per second. This was the most accurate measurement to date. Michelson continued his work collaborating with Edward Morley, a chemist, in a series of famous experiments, most notably the Michaelson-Morley experiment of 1887. While this particular experiment's primary goal was to detect the luminiferous ether, which will be discussed in the next chapter, its precision in optical measurement was unparalleled for its time. Michelson's continued efforts to refine the speed of light measurement led to even greater accuracy. In the 1920s, Michelson undertook his most ambitious measurements. He conducted experiments over very long distances, using large rotating mirrors and precise timing equipment. One of his most famous experiments involved measuring the speed of light between two mountain peaks in California, Mount Wilson and Mount San Antonio, also known as Mount Baldy. The distance between these two peaks was approximately 35 kilometers, about 22 miles. He used a powerful light source and a system of rapidly spinning octagonal mirrors with 8 sides. The light would travel from Mount Wilson to a mirror on Mount San Antonio and reflect back to Mount Wilson, where it would strike the rotating octagonal mirror again. By precisely adjusting the rotation speed of the octagonal mirror until the returning light beam was perfectly reflected to the observer, Michelson could calculate the time of travel and thus the speed of light. He used vacuum tubes over a portion of the path to minimize the effects of air, further enhancing accuracy. His measurements from 1926 gave a value of 299,796 kilometers per second, 186,284 miles per second. Michelson continued to strive for even greater precision, conducting experiments in a long vacuum tube at the Irvine Ranch near Santa Ana, California, during the 1930s. This final set of experiments, interrupted by his death in 1931 and completed by his colleagues, aimed to eliminate the effects of atmospheric variations on the light path. These later measurements, along with others performed by different scientists around the world using various techniques, such as Kerr cells and electronic methods, consistently converged on a highly precise value. By the mid-20th century, with the advent of radar and microwave technology, new methods for measuring the speed of electromagnetic waves, of which light is a part, emerged, offering even greater accuracy. These methods, often relying on the precise measurement of frequencies and wavelengths, further refined the value of c. The pursuit of the speed of light culminated in 1975, when the International Bureau of Weights and Measures formally adopted a value for the speed of light in a vacuum, 299,792,458 meters per second. This value was so precise that in 1983, the meter itself was redefined in terms of the speed of light. The meter is now defined as the distance light travels in 1,299,792,458th of a second. This means that the speed of light in a vacuum is now a defined constant, not something that needs to be measured repeatedly. Instead, measuring the speed of light is equivalent to measuring the length of the meter. The 19th century was a period of immense scientific progress, particularly in the understanding of electricity, magnetism, and light. As scientists began to grasp that light exhibited wave-like properties, a fundamental question arose. If light is a wave, what is it waving in? Just as sound waves require a medium like air or water to travel, and water waves require water, it seemed logical that light waves too must propagate through some kind of substance. This led to the widespread adoption of the concept of the luminiferous ether. The luminiferous ether, often simply called the ether, was a hypothetical medium proposed to fill all of space. Its primary purpose was to provide a physical medium for the propagation of light waves. For many scientists of the time, the idea of waves travelling through an absolute vacuum seemed counterintuitive, even impossible. Waves, by definition, were disturbances in a medium. Without a medium, how could light waves exist or travel across the vast emptiness between stars and planets? The concept of an ether was not entirely new. As far back as ancient Greek philosophy, thinkers like Aristotle had proposed the existence of an ether as a fifth element, a pure, unchanging substance that filled the heavens and was distinct from the four earthly elements. In the 17th century, René Descartes, while believing light was instantaneous, imagined a plenum, or subtle fluid filling space that transmitted light as a pressure. Isaac Newton also toyed with the idea of a subtle ether, though he did not firmly commit to it for light propagation. However, the luminiferous ether of the 19th century was a much more specific and physically defined entity, necessitated by the growing evidence for light's wave nature. The early 19th century, particularly with the work of Thomas Young and Augustin Jean Fresnel, provided strong experimental support for the wave theory of light. Young's double-slit experiment clearly demonstrated interference patterns, a hallmark of wave behaviour. Fresnel's mathematical descriptions of diffraction and interference further solidified the wave model. If light was indeed a wave, then the ether became a crucial component of the physical picture. Scientists began to attribute very specific properties to this hypothetical ether to explain light's observed characteristics. First, for light to travel at such an incredibly high speed, the ether had to be extremely rigid or stiff, like a solid, yet also perfectly elastic. A very rigid medium would allow for rapid transmission of vibrations. Second, the ether had to be incredibly tenuous and massless, offering no resistance to the motion of celestial bodies. Planets and stars moved freely through space for billions of years without any noticeable drag. If the ether were dense or viscous, it would slow them down, which was clearly not observed. Third, it had to be completely transparent and undetectable by any means other than the propagation of light itself. It filled everything, yet it was invisible and insensible. The properties required of the ether were therefore quite contradictory. It had to be a rigid solid to transmit transverse waves. Light waves were understood to be transverse, vibrating perpendicular to their direction of travel, at enormous speeds, but also completely frictionless and massless, to allow objects to move through it unimpeded. This paradox began to pose significant theoretical challenges as the 19th century progressed. One of the central assumptions of the ether theory was that the ether provided an absolute reference frame for light. This meant that the speed of light, denoted as c, would only be c when measured relative to the stationary ether. If an observer or a light source was moving through the ether, then the measured speed of light would appear different, either faster or slower, depending on the observer's motion relative to this stationary ether. This was analogous to sound waves. The speed of sound is constant relative to the air, but if you measure the speed of sound from a moving car, it will appear different depending on your motion relative to the air. This concept led to the idea that it should be possible to detect Earth's motion through the ether. Earth orbits the Sun at a speed of approximately 30 kilometers per second, about 18.6 miles per second. If the ether was stationary, then as Earth moved through it, there should be an ether wind blowing past Earth, similar to how a moving car experiences a wind even on a calm day. This ether wind should affect the measured speed of light depending on the direction of measurement. For example, light travelling in the direction of Earth's motion through the ether should appear slower, while light travelling against the ether wind should appear faster. This theoretical prediction spurred several experimental attempts to detect the ether wind. The most famous and meticulously performed of these experiments was conducted by Albert Abraham Michelson, an American physicist, and Edward Morley, an American chemist and physicist, in 1887. Their collaboration in Cleveland, Ohio, aimed to directly detect the relative motion of Earth through the luminiferous ether. The Michaelson-Morley experiment was designed with extraordinary precision. It utilized an interferometer, a device Michelson had invented, which could detect extremely tiny differences in the speed of light over different paths. The core idea of the interferometer was to split a single beam of light into two beams that travelled along different paths, then recombine them. If the speed of light changed along one path due to the ether wind, it would cause a phase difference between the two recombined beams, resulting in an observable interference pattern, alternating bright and dark fringes that would shift as the apparatus was rotated. The interferometer was set up on a massive stone slab, floating in a pool of mercury. This allowed the entire apparatus to be rotated smoothly and precisely, so that the two light paths could be oriented in different directions relative to Earth's presumed motion through the ether. One arm of the interferometer would be aligned parallel to Earth's motion and the other perpendicular to it. According to the ether theory, light travelling along the parallel arm would be affected by the ether wind, experiencing a slight delay in its round trip compared to light travelling along the perpendicular arm. This difference in travel time, though extremely small, was calculated to be detectable by their sensitive instrument. Michelson and Morley carefully performed their experiment, rotating the apparatus and making observations over many hours and at different times of the year, to account for Earth's changing direction of the motion in its orbit. To their astonishment, and to the astonishment of the scientific community, they found no detectable shift in the interference pattern. Regardless of the orientation of the apparatus or the time of year, the speed of light appeared to be the same in all directions. The result of the Michelson-Morley experiment was a profound puzzle. It implied that there was no ether wind, and therefore no stationary ether through which Earth was moving. The experiment's null result directly contradicted the prevailing ether theory, and the idea that the speed of light should vary depending on the observer's motion relative to a fixed medium. It was one of the most significant negative results in the history of science, leading to a crisis in physics. Various attempts were made to explain away the null result while preserving the ether concept. One famous proposal came from George Fitzgerald, an Irish physicist, and Hendrik Lorentz, a Dutch physicist. They independently suggested that objects moving through the ether would physically contract in the direction of their motion, and that clocks would slow down, in just such a way as to precisely cancel out the expected effect of the ether wind on light speed. This Lorentz-Fitzgerald contraction was an attempt to save the ether theory by introducing new, unproven physical effects. While these mathematical transformations, now known as the Lorentz transformations, would later become fundamental to special relativity, their original motivation was to preserve the ether. Another idea was that the ether was somehow dragged along by moving objects, so that Earth carried its own local pocket of ether, meaning there would be no relative motion to detect. However, this ether drag hypothesis was contradicted by other astronomical observations, such as stellar aberration, which required light to come from distant stars through an ether that was not dragged by Earth. The Michaelson-Morley experiment's failure to detect the ether wind gradually led many physicists to question the very existence of the luminiferous ether. The properties required for the ether were becoming increasingly contradictory and complex, stretching the limits of believability. It needed to be a perfect fluid for celestial motion, but a perfectly rigid solid for wave propagation. It had to be ubiquitous yet undetectable. The elegant simplicity of light travelling without a medium began to seem more plausible than the increasingly contrived properties of the ether. The definitive solution to the ether problem came with Albert Einstein's special theory of relativity, published in 1905. Einstein's theory completely discarded the concept of the luminiferous ether. Instead, he based his theory on two fundamental postulates. The first postulate stated that the laws of physics are the same for all observers in uniform motion, inertial frames of reference. The second and revolutionary postulate stated that the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. Einstein's second postulate directly explained the null result of the Michaelson-Morley experiment without needing any ether or ad hoc contractions. If the speed of light is truly constant for everyone, no matter how fast they are moving, then there is no need for a special medium or a preferred reference frame. The ether, having no observable effect and leading to theoretical contradictions, became unnecessary. Einstein's theory provided a simpler, more elegant explanation for why the speed of light appears constant. The abandonment of the ether concept was a profound paradigm shift in physics. It meant that light, unlike other waves familiar at the time, did not require a medium to propagate. It was an electromagnetic phenomenon that could travel through the emptiness of space by virtue of oscillating electric and magnetic fields. This was a radical departure from classical physics, which always sought a mechanical explanation or a medium for wave propagation. The demise of the ether had far-reaching consequences. It cleared the way for a deeper understanding of the fundamental nature of space and time themselves. Without a preferred ether frame, all inertial reference frames became equivalent, leading to the mind-bending consequences of special relativity, such as time dilation, time slowing down for moving objects, and length contraction, objects appearing shorter in the direction of a motion, which were no longer seen as physical changes to objects but as consequences of the very nature of space-time. The late 19th century was a period of intense scientific inquiry, particularly concerning the nature of light and the medium through which it was believed to travel. By this time, the wave theory of light had largely triumphed over the particle theory, primarily due to compelling experimental evidence such as Young's interference patterns and Foucault's measurements showing light travels slower in water than in air. With light firmly established as a wave, the prevailing scientific consensus held that, like all other known waves, light must propagate through some kind of medium. This hypothetical, invisible and all-pervading substance was termed the luminiferous ether. The luminiferous ether was envisioned as the universal medium for light waves. Scientists believed it filled all of space, permeating even the vacuum, and provided the necessary substrate for light to travel from the Sun to the Earth and across vast interstellar distances. A key assumption of the ether theory was that this medium was stationary, providing an absolute reference frame for the universe. This meant that the speed of light, measured relative to this stationary ether, would always be a constant value. However, if an observer, like Earth, was moving through this stationary ether, then the measured speed of light should appear different, depending on the direction of Earth's motion relative to the ether. This expected variation in light speed due to Earth's movement through the ether was referred to as the ether wind. The Earth orbits the Sun at a considerable speed, approximately 30 kilometers per second, or about 18.6 miles per second. If the ether was indeed stationary, then as Earth moved through it, there should be a detectable ether wind blowing past Earth. This would be analogous to a boat moving through water. Even if the water itself is still, the moving boat experiences a flow of water relative to it. Detecting this ether wind became a major scientific goal, as it would provide direct evidence for the existence of the ether and confirm its role as the universal medium for light. Among the scientists eager to detect this elusive ether wind was Albert Abraham Michelson, an American physicist who lived from 1852 to 1931. Michelson was an expert in optics and interferometry, the science of using interference patterns of light waves to make precise measurements. In 1881, while working in Germany, Michelson designed and built an apparatus specifically for detecting the ether wind. This initial experiment, though innovative, suffered from some limitations in sensitivity. It suggested no significant ether wind, but Michelson himself concluded that its precision was not high enough to definitively rule out the effect. Michelson returned to the United States and, in 1887, collaborated with Edward Morley, an American chemist and physicist who lived from 1838 to 1923 at the Case School of Applied Science in Cleveland, Ohio. Together, they designed and conducted a much more sensitive and refined version of the experiment, which became famously known as the Michaelson-Morley experiment. Their goal was clear: to precisely measure the tiny variations in the speed of light that would be caused by Earth's motion through the stationary luminiferous ether. The core of their experimental setup was a device called an interferometer. Michelson's interferometer worked on the principle of splitting a single beam of light into two separate beams, sending them along different paths, and then recombining them. If the two beams travelled at slightly different speeds, or if one path experienced a greater delay than the other, it would cause the waves to be out of phase when they recombined. This phase difference would manifest as a shift in the interference pattern observed through a telescope. An interference pattern is a series of alternating bright and dark lines or fringes, created when two light waves either reinforce each other, bright fringes, or cancel each other out, dark fringes. Here is a simplified description of the Michelson-Morley interferometer. A single beam of light from a powerful source was directed towards a semi-silvered mirror, also called a beam splitter. This mirror was designed to transmit about half of the light and reflect the other half. The reflected part of the beam travelled along one arm of the interferometer to a fully silvered mirror, mirror 1, at a certain distance, then reflected back to the beam splitter. The transmitted part of the beam travelled along a perpendicular arm to another fully silvered mirror, mirror 2, at an equal distance, then also reflected back to the beam splitter. When both reflected beams returned to the beam splitter, they were recombined and directed towards a telescope where the interference pattern was observed. The genius of the setup lay in its sensitivity to relative changes in the speed of light. If Earth was moving through the ether, then the speed of light along the arm parallel to Earth's motion would be affected by the ether wind. Light travelling against the wind would be slowed down, and light travelling with the wind would be sped up. The round-trip time for this parallel arm would be slightly longer than if there were no ether wind. In contrast, light travelling along the perpendicular arm would be less affected by the ether wind, or affected in a different, typically smaller way. This small difference in travel time between the two arms, caused by the hypothetical ether wind, would result in a detectable shift in the interference fringes when the apparatus was rotated. To maximise the sensitivity and ensure that even a tiny effect could be detected, Michelson and Morley took extraordinary measures in their experimental design. First, they extended the effective length of the light paths by using multiple reflections. Each arm of the interferometer was designed with several mirrors, causing the light to bounce back and forth multiple times within each arm, effectively increasing the path length from about 11 metres, about 36 feet, to 65 metres, about 213 feet. This magnified any potential time difference. Second, to eliminate vibrations and temperature changes that could affect the delicate measurements, the entire optical apparatus was mounted on a massive stone slab. This slab measured about 1.5 metres, about 5 feet, square and 45 centimetres, about 18 inches, thick. Third, this heavy stone slab was floated in a trough of liquid mercury. This allowed the entire apparatus to be rotated smoothly and continuously, without introducing vibrations or distortions. The mercury bath provided a nearly frictionless bearing, enabling the researchers to rotate the interferometer slowly and observe any shifts in the fringe pattern as its orientation to the presumed ether wind changed. The experiment was carried out over several days and nights in July 1887. Michelson and Morley repeatedly rotated the interferometer through a full 360 degrees, observing the interference fringes through the telescope. According to the ether theory, they expected to see a measurable shift in the interference pattern as the arms aligned with and against the direction of Earth's motion through the ether. The predicted shift was small, but well within the capabilities of their highly sensitive instrument. To their profound surprise, and to the astonishment of the scientific world, Michelson and Morley observed no significant shift in the interference fringes. Regardless of the orientation of the apparatus or the time of year, which would change Earth's direction relative to any fixed ether. The speed of light appeared to be the same in all directions. There was no detectable ether wind. The result was a null result. The expected effect was simply not there. The significance of this null result was immense. It directly contradicted the prevailing ether theory, which had been the cornerstone of light propagation for decades. If the ether existed and was stationary, the effect should have been observed. The failure to detect an ether wind meant that either the ether did not exist, or it possessed properties so bizarre as to make it undetectable, or light itself behaved in a fundamentally different way than previously imagined. The Michaelson-Morley experiment created a major crisis in physics. Scientists grappled with various explanations to reconcile the null result with the assumed existence of the ether. One hypothesis was ether drag, suggesting that Earth somehow dragged the surrounding ether along with it. However, this was contradicted by astronomical observations like stellar aberration, which showed that starlight, when entering Earth's atmosphere, behaves as if it's coming from a source whose apparent position shifts due to Earth's motion, implying the ether is not dragged along by Earth. Another, more famous attempt to explain the null result while preserving the ether came from George Fitzgerald, an Irish physicist, and Hendrik Lorentz, a Dutch physicist. They independently proposed that objects moving through the ether would physically contract in the direction of their motion, and that clocks would slow down in precisely the right amounts to cancel out the expected effect of the ether wind. This Lorentz-Fitzgerald contraction was a clever mathematical fix to make the ether theory consistent with the experimental result. However, it seemed rather ad hoc, lacking a deeper physical explanation for why objects should contract or clocks should slow down when moving through this unseen medium. Despite these attempts, the ether theory began to crumble under the weight of the Michaelson-Morley experiment's findings. The properties required for the ether became increasingly contradictory. It had to be a rigid solid to support transverse light waves at incredibly high speeds, yet completely frictionless and massless to allow planets to move through it without resistance. The idea of a medium that was everywhere and affected everything, yet was utterly undetectable, became less and less tenable. The true resolution to the ether puzzle came in 1905 with Albert Einstein's special theory of relativity. Einstein, who lived from 1879 to 1955, famously disregarded the need for an ether altogether. Instead, he based his theory on two revolutionary postulates. The first postulate stated that the laws of physics are the same for all observers in uniform motion, meaning moving at a constant speed in a straight line. The second postulate, and the key to understanding the Michaelson-Morley result, stated that the speed of a light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. Einstein's second postulate directly explained why Michelson and Morley found no ether wind. If the speed of light is a universal constant, fixed at approximately 299,792,458 meters per second, for all observers, then there is no need for a preferred medium or an absolute reference frame like the ether. The constant speed of light is a fundamental property of the universe itself, not dependent on any medium through which it travels. The Michaelson-Morley experiment therefore did not merely fail to detect the ether, it provided crucial empirical evidence that supported the radical ideas that would later form the bedrock of modern physics. Its null result was not a failure of the experiment, but a triumph of scientific inquiry, as it forced a fundamental rethinking of space, time, and the nature of light. It paved the way for Einstein's theory of relativity, which fundamentally changed our understanding of the cosmos and established the speed of light not just as a very fast constant, but as an ultimate cosmic speed limit inherent to the fabric of space-time. The experiment stands as one of the most important experiments in physics, not for what it found, but for what it did not find, thereby opening the door to a new era of physics.